Yeah, welcome back. So today I'm going to tell you the story that the performance of fading channel is very bad compared to AWGN channel. So how to enhance the performance of fading channel is the story today. So one technique is called diversity. If you do a diversity techniques, the performance of fading channel will be improved. Okay, so diversity mean we send the information independently faded path to the receiver, such that the probability of at least one of the path is better will be there. So we will the receiver is able to receive the signal. Okay, so the independently faded path can be a different time, or it can be a different frequency, or it can be different space as well. So that's called antenna diversity. So from transmitter to receiver, we send the same information independently faded channel such that at least one of the path will be good, and we will be able to receive the signal. So that's what is diversity basically meaning. So the main story, communication over fading channel has a poor performance due to significant probability the channel is in the deep fade. Okay, so deep fade mean, so let's say this is the channel quality versus time. Okay, the channel quality, sometime, as I said, the signal will receive constructively, so you have a channel quality very good, and sometimes it's go destructively, sometimes it's go like this. So let's say this is the threshold. So this is called deep fade. Okay, this is called deep fade. So during this deep fade, we may lose the information. So this is the case for the fading channel. Okay, this is the case for fading channel. Okay, but AWGN channel, we get bit rate due to noise, but most probably the fading channel we get bit rate due to deep fade. Okay, deep fade. Okay, so we need to do something about during this deep fading condition. So, okay, so that's what we are going to talk about. So communication over fading channel is a poor performance due to significant probability that channel is in the deep fade. So reliability is increased by providing more resolvable signal path that fade independently. So we try to send the information independently faded channel to the receiver. So basically, the probability of at least one of the channel is better is there. So we will be able to receive the signal. Okay. So diversity can be provided across time and frequency and space as well. So the time diversity, you need to do coding and interleaving. Frequency diversity is you send the information different frequency. Frequency selected channel have a frequency diversity already inherent in the channel. Space diversity is the one MIMO techniques. Okay, MIMO technique will provide space diversity. So name of the game is to how to exploit the added diversity in an efficient manner. Okay, as I said, in the frequency selected channel, the diversity is already there. And also the MIMO channel, the space diversity is already there. So the name of the game is to how to exploit the added diversity in an efficient manner. So let's compare the fading channel performance and AWGN channel performance. So AWGN channel, you may see this one in the basic digital communication course. The receive signal is a receive signal at the receiver. So you have a transmitter here, TX. You have a receiver signal here, a receiver here, RX. So this is AWGN channel. the received signal y is equal to x plus w. Okay, there's no fading. There's no fading. So there's no fading mean there's no channel coefficient in front of the. This is the transmitter signal x. This is the received signal y, and this is the noise. Okay, so if you consider BPSK modulation, the the transmitted signal can be plus or minus a, and the probability of error is given by this Q function, which is given by square root of 2 SNR. Okay, SNR is signal to noise ratio, which is a squared over n naught. So this guy. This W is distributed as complex normal, zero mean, variant n naught. Okay, and so the SNR is signal to noise ratio is a squared over n naught. So the probability of error for the BPSK signal in the AWGN channel is given by this. Okay, so this is the Q function. Q function is a complementary cumulative distribution function. So the CCDF, complementary cumulative distribution function, this is Q function. So the QA, let's say, goes exponentially, okay, decrease exponentially. Okay, Q0 is half, and Q1, okay, you see Q0, the QA is defined as the probability x greater than a. So this is, it's a normal distribution with the variant 1 and 0 mean. So this is 1 over square root of 2 pi exponential minus x squared over 2 dx. Okay, so this is goes from a to infinity. So this is the Q function, and Q0 is half actually, and if you have a Q1, it is like a 0.159, and Q2 it is going to be like 0.00135. So why I'm writing this is going exponentially decay. Okay, this is exponentially decaying, and the probability of error for the AWGN channel is going to decay exponentially as well. For probability of error is going to decay exponentially with respect to SNR. Okay, so this is the main message for the AWGN channel. Okay, so the probability of error is Q square root of 2 SNR. SNR is sigma square, a squared over n naught. The Q function is the complementary cumulative distribution function of the zero mean standard normal distribution, zero mean variant 1, and the message is the probability of error decrease exponentially. Okay, that is the message. But if you will see soon, for the fading channel, the probability won't decrease exponentially. It will go 1 over SNR. Okay, so that is the problem. The probability of error for the fading channel is very bad. That's why we need a diversity techniques. Okay, so in order to prove this one, the next slide, how do we get this probability of error is shown in the next slide. Okay, so here the error probability decay exponentially with SNR. So that's what I said. The error probability decay exponentially with SNR. This is the case for the AWGN channel, and this is for the fading channel. Okay. So, so this is the Gaussian detection for the AWGN channel. Okay, so let's say there are two signals sent BPSK, UA and UB. So this may be a, and this guy may be a, and this guy may be minus A. So plus or minus A is sent. The received signal PDF, if UB is sent, the received signal PDF is given by this plot here. Okay, if UB is sent, the receive signal PDF is given in the right-hand side. Okay, so left-hand side. So this is the PDF. If we send a UB, if you send a UA, this is the PDF, and if you send a UB, and this is the PDF. Okay, so the receiver, if the receive signal is greater than this point, this is the threshold. If the receive signal is greater than this side, we choose, the receiver is choose UB is sent. If the receive signal is fall this side, we choose, the receiver will choose UA is transmitted. So this is the way the probability of error calculation normally happen. So I'll tell you. So the probability of error, so let's say, is given by the probability y is less than UA plus UB over 2, given that UA is transmitted. Okay, UB is transmitted. So UB is transmitted, but the Y is UB is transmitted, but UB is transmitted, Y is in the other side, then you make a probability of error. So this is exactly same as, okay, the probability, this is a receive signal, Y is equal to X plus W. If the W is greater than UA minus UB over 2. So this is, so the UB minus UA over 2 is this guy. Okay, if the noise is bigger than UA minus UB, this is a mod here, or UB minus UA, whatever. So if this is the case, you make a error. Okay, if the noise is larger than this guy, so this is the UB minus UA. Okay, so half of that. If the noise is bigger than this, you make an error. Okay, so this is the, I told you this W guy is the distributed as complex normal, 0 mean N naught. So probability of this is Q function. It can be UB minus UA. Oh, okay. So this is going to be UB minus UA over 2. So this is going to be, and we need to divide it by square root of N naught over 2. So this is N naught over 2 actually. So in this case, you will get UB minus UA is actually 2A over 2 N naught over 2 square root, and this turned out to be Q function 2 SNR. So this is the kind of a proof for the this equation. This equation. Okay, SNR is A squared over N naught. Okay, so if the W, the noise is bigger than this value, it will flip the receive signal, then you will make an error. So the probability W greater than this is a Q function. Q function is based on standard normal, but so that's why we need to divide by N naught over 2. So it turned out to be like this. So this is the way the probability of error is derived. Anyway, so let's say fading channel. For relay fading channel, the receive signal is Hx plus W. So the fading channel, so there is a transmitter here, and this is the receiver here, Rx, and this is the channel here. This is the channel here. The receive signal now written as Hx plus W. The receive signal is Hx plus W. H is the channel fading coefficient. Okay. So again, same X plus or minus A. Coherent detection. What is coherent detection mean? The receiver, we assume the receiver know the channel. If the receiver know the channel, we say it's a coherent detection. If receiver does not know the channel, we try to detect the signal. That's called non-coherent detection. So coherent detection in all our wireless communication, your 4G, 5G, everything is work based on coherent detection. The base station and the users normally estimate the channel, okay? So it's a coherent detection. Condition on edge, the probability of error is given by this expression here, okay? So if you see the probability of error here, this term, the new term came here for the fading channel. If you for the AWGN channel, you see the probability of error. There's no fading coefficient here. It's 2 SNR. But for the relay fading channel, there is a channel coefficient. This guy is a random. This guy is a random. So I told you yesterday, this guy is a relay distribution. The squared magnitude is a exponential distribution. Okay, so this guy is a exponential distribution, random variable. Okay, we saw yesterday this H is relay distribution, and this H squared is an exponential distribution. So with the parameter 1. So if you do integration with respect to exponential distribution, and you will get probability of error is equal to this. Okay, so we have one tutorial question how to derive from here to here. It's a very complex derivation from here to here. So if you take average over H squared is exponential distribution. If you take average over H, that's exponential distribution, you will get this probability of error. And in the communication, we normally talk about high SNR regime and low SNR regime. Okay, so for in the case of so the probability of error goes here like this versus SNR. For the fading channel, it goes like this. This is the AWGN channel. This is fading channel. Okay, so this region is called high SNR. Okay, high SNR. And this region we call low SNR. Okay, low SNR. So in high SNR, you can show the probability of error is 1 over 4 SNR. Okay, so that's what I told you. This guy is reducing 1 over SNR, but here AWGN channel, the probability of error reduce exponentially. So we will see some question in the afternoon how to go from here to here and from here to here. So these are it's not easy to prove. These are very complex derivations. Anyway, so here is the relay fading versus AWGN performance for the probability of error. So you can see this is the probability of error for the AWGN channel. You can see it's decreasing very, very exponentially. For the fading channel, the probability of error is very bad. Okay, so there are coherent detection is here. Coherent detection assume channel is known at the receiver. There's non-coherent detection also there, assuming there's no channel knowledge. Okay, so if you see 10 to the minus 3, let's say 10 to the minus 3 probability of error. For 10 to the minus 3 probability of error mean you send 1,000 bits, only 1 bit is error. So that's mean 10 to the minus 3. Okay, so for the 10 to the minus 3 probability of error, the SNR required here is something around 7 dB for AWGN channel. Okay. Similarly, for the fading channel, if you go here, it is something like 24, something like that SNR. So there is a gap between. So if you go 10 to the minus 3, 10 to the minus 3 mean you send 1,000 bits, only 1 bit is error. For the AWGN channel, it's like a 7 dB. You need a 7 dB SNR. But for the fading channel, it's something like the 24 dB SNR. So the gap between here is something 17 dB gap in between. So 17 dB more power you need to get, there's a difference between 17 dB. So 17 dB is very huge, okay? 3 dB mean you are doubling the power, but 17 dB is, it's a huge gap. So that's why we need a diversity techniques, okay? So to get a, 10 to minus 3 bit rate, AWGN channel need a 7 dB, but fading channel need a 24 dB. So there is a gap between SNR is 17 dB, which is very high. So we need diversity techniques to bring this guy very close to here. So the fading channel sometime even beat AWGN channel if we do some clever techniques. So that's what we are going to look at it. How do we bring this bit error curve closer to AWGN channel for the, so how to bring the fading channel performance very closer to AWGN channel. So that's why we need diversity. Okay. So typical error event. So this is the probability of error for the fading channel. So if this condition happened, h squared is greater than 1 over SNR, error probability is very small. So this is the condition, we are not in the deep fade. Okay, h squared, the channel between the transmitter and receiver is very large compared to 1 over SNR, then the probability of error is very good. Okay, but if you see this condition, h squared is very less compared to 1 over SNR, we are in a deep fade situation, we will get the probability of large probability of error. So probability of this event, okay, probability of this event is we can prove in the one of the tutorial question is 1 over SNR. As I said, this guy is distributed as exponential distribution. We can prove that is 1 over SNR. Okay, so the message of this slide is this condition is for good small probability of error. This condition for deep fade situation. In that case, we have a larger probability of error. So in the fading channel, we are getting error because not our noise is large. It's not like that. We are getting an error because we are in a deep fade. Okay, AWGN channel, we are getting an error because of noise is large. So there are two different situations for the error compared to AWGN and fading channel. Okay, so that's what it's saying here. Typical error event is due to channel being in deep fade rather than noise being large. So this is the good message, the story, important message of this slide, okay? For the fading channel, the typical error is due to channel being in deep fade rather than noise being large. But we get AWGN channel, we are getting a error because of the noise is large. But the fading channel, we are getting error because of we are in deep fade. Maybe I'll skip this slide. So, okay, so here is first I'm going to talk about time diversity. So what is time diversity? So anybody heard about interleaver? Interleavers? Yeah? Did you heard about the word interleaver? Okay, so so what is this slide is saying? Time diversity can be obtained by interleaving and coding over symbol across different coherent time. So this plot is showing the channel condition between transmitter and receiver. Let's say there's a transmitter here, and let's say there's the receiver here, there's a channel here, okay? This channel, as I said yesterday, is a random. This channel is random. Take one random realization and stay for constant period. What that period is coherent time. And then take another random realization, stay constant period for coherent time, etc. So that's what is shown here. So take a random realization, stay constant period, which is the coherent time. This is the coherent time. And then take another random realization, stay constant time, coherent time, and take another random realization. So this is, we are in deep fade here. So here you see we are in a deep fade. And then take another random realization and to stay constant. Okay, so this is the way the channel behave. Okay, so if you send information from here to here, so here in this, okay, so normally communication, what happen is you have some image or video or whatever you wanted to send from here to here, base station user to the base station, let's say. You code those things, information using LDPC or turbo code. So you have a code word. You have a code word you send through the channel. Okay. If you, so here there's no interleaver. You send that code word through this from transmitter to receiver. Here you are in a good channel condition. No problem. You will receive. Here also almost a good channel. You will receive. But here you are in a bad channel. So your entire code word is not going to be received here, and you will lose that code word, okay? And then the next code word also, we are in a good channel, we will be going there. So if we don't do any other clever techniques, in this case interleaver, if you don't do interleaving, that's why I'm saying no interleaving, this you are in a deep fade, you will lose the entire code word, okay? But if you do an interleaver, so what does that interleaver mean? So let's say you need you wanted to send 16-bit, let's say your code word have a 16-bit, okay, let's say 1-bit, 2-bit, let's say 3-bit, up to 16-bit. You send this 16-bit through this channel, okay? So this is your code word, okay? Without interleaving, you send this. But interleaver mean you put this 16 code word like this, 1, 2, 3, 4, 5, 5th bit, 6th bit, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 bit. You arrange the 16 bit like this. You're not going to send serially 1, 2, 3, 4 bits to here. Instead of sending that, you send like this. You send 1 bit, 5th bit, 9th bit, 13 bit, and then you go back to 12-bit, 6-bit, 10-bit, 14-bit, and then you go back to, so you send like this. So you scramble the information like this. This is called interleaver. So you interleave and you send different order compared to this. So if you do an interleaver like this, okay, what happen is, this code word going through, there are, let's say, 4 portion of that code word going through different channel. So the first code word will, first portion of the code word will go through this channel. The second portion of the code word will go through this channel. The third code word of the will go through this channel. The fourth portion of the code word go to this channel. By doing so, what happen is, this is the interleaved case. Okay, your all code word is divided by 4. Half, 1/4 of the code word going through independently faded channel. Okay, that's what diversity means. You need to send the information through independently faded channel. So your entire code word is divided by 4 by interleaving and sent through independently faded channel. Okay, but here again you are in the deep fade. You will lose entire portion of the communication. But what happened here is each of the code word, only 1/4 of the information is lost. Okay, here your entire code word is lost if you don't do interleaver. But here, if you do interleaver, each of the code word, 1/4 of the information is lost, and 3/4 of the information is received in your entire code word. That's good enough. If we use 5G is using LDPC and turbo code, these code words are very powerful code words. If the code word, if you lose only 1/4 of the information, this code word will correct, okay? So only if you lose 1/4 of the information, does not matter, this LDPC code and turbo code will correct the information. So that's what, This is called time diversity. So time diversity is achieved by interleaving and coding, okay? So your code word is going through independently faded channel such that even though you are in the deep fade, only some of the portion of the information is lost, and you will be able to recover entire code word using powerful codes like LDPC and turbo codes. Okay, so that's the message about time diversity. So time diversity is achieved by interleaving and coding. So coding alone is not sufficient. It's saying coding alone is not sufficient. You need interleaver as well. Here, you do only coding, but you need an interleaver to get the time diversity. Okay. So next, I'm going to talk about repetition code. So what is this repetition code is saying is, you send the information again and again in a different coherent time to get the diversity. So actually, this is repetition code is a very inefficient techniques because you need to repeat again and again, send the same information through independent faded channel. So by doing so, your spectral efficiency is very no good. So, but for the theory, people teach repetition code, but in practice, we are not implementing repetition code very often. Okay, so this is that's what I'm going to show you in the next two slides. Okay, so simplest code is called repetition code. After interleaving over L coherent time, the received signal is given by here. So repetition code, so you repeat the same information again and again for different independent faded channel. Then your received signal is given by this, okay? So this is the vector now, okay? This is the vector received signal, and this is the channel, and this is the noise. The same information is repeated L time, okay? Same information is repeated L independently faded channel, and you receive here. So here is the vector. This is the vector channel, okay? So so the H is now is a vector, H1 up to HL, okay? So in this case, this guy is distributed as chi-square distribution with 2L degree of freedom, okay? So, so this is a very complex distribution. You will see in the tutorial the distribution is given. For the vector channel, this guy is no longer exponential, okay? Only one variable, this is exponential. For the vector case, this is not exponential. This is a chi-square distribution with a 2L degree of freedom. And analyzing the performance for the vector channel, things are not easy, okay? Anyway. So this is a classical vector detection in wide Gaussian noise. So how do we do that here? So you have a receive signal here, Y, and this is your UA and UB, and you project this receive signal towards this, this line, and this is your Y tilde. This Y tilde is a sufficient statistics to detect whether we send UA or UB, okay? So let's say UA is A into H, UB is A minus A into H, okay? So the BPSK modulation. So your receive signal is projected through this line, and how do you do that projection? You multiply the receive signal by its channel complex conjugate divided by channel magnitude. So this is called match filtering, okay? There are many names for this one. This is called match filtering, coherent combining, and receiver beamforming, etc. There are many names for this one, okay? So this is, let's say, by multiplying the channel coefficient by divided by its magnitude is called match filtering. So this guy is a sufficient statistics to detect whether UA is transmitted or UB transmitted. Okay. So now in this case, so your received signal is y is equal to hx plus w. You multiply the received signal and you get y tilde by your conjugate over h into y. So by doing so, your equation is going to be like this. Okay, so it's going to be reduced to this equation. So this is this slide is this point is saying reduced to a scalar detection problem, and you can now detect. Okay, so by doing so, so how do we get this one? So how do I get this one? Because if you multiply by this, what happened is H Hermitian conjugate. There is Hx here. And this guy is nothing more than squared, and one of them is cancelled, and you get this equation. And we call this is as a tilde, W tilde, and W tilde and W distribution won't change. It's going to be 0 mean, let's say, n node over variant. By doing conjugate and divide by its magnitude, your distribution is not going to change. This distribution and the distributions are same, so the probability analysis is going to be not be affected by multiplying the conjugate of the channel divided by its magnitude. The distribution won't change. Anyway, so by doing so, I told you this guy is exponential distribution, chi-square distribution. So the chi-square distribution curves are like this. So if you have a so this H is now H1 up to HL, okay? So this, I told you this guy is now chi-square distribution with 2L degree of freedom. This plot is showing different distribution for different L, okay? So L is equal to 1 is the exponential distribution, and then L is equal to 2, this is the distribution, etc. And you can see the probability of error. I told you this is the condition to get the probability of error. The chi-square distribution can be approximated such that you will be able to prove the probability of error can be approximated as like this. Okay? So when you have a probability of error like this, the SNR to the power L, this guy, is called diversity order. So this guy is called diversity order. Okay? So if you have a L channel, your information is sent through different L path, so you get diversity order L. So this is the proof. Okay, so we have a tutorial question to prove this one as well. So this is the diversity order. Okay, SNR to the power L. When you derive the probability of error equation and you see what is the power of SNR, this will give you the diversity order. Okay, diversity order. So that means your signal is go through L independently faded channel. And then the probability of error curve looks like this. I told you for the fading channel that if there's no diversity, the probability of error goes like this. The slope is 1 over SNR. Here, the slope is 1 over SNR to the power squared. So the slope is 1 over SNR to the power 3. By doing diversity, you see we are bringing the probability of error curve closer to, towards at least to the AWGN channel. So by doing diversity, we are bringing this curve closer to SNR. So if you send information through different independent faded channel, you are bringing the curve closer to AWGN channel. So that's the proof here the probability of error is 1 over SNR to the power L. So L is actually the diversity order. Okay, so I'll skip this one. So now next, I'm going to talk about any questions so far? Any question? Oh, yeah. Yeah, L is equal to 4. Yeah. Yeah. In that case, the diversity order is 4. Yeah. Yeah. Okay, so that's a good question. So you're asking which L is going to be, I think it's going to be a very large number of L. So yeah, okay, so yeah. It's going to be very large, yeah. We can go and see. So you can see this is the AWGN channel. 10 to the minus 8 bit rate is like 12 dB or something like that. Okay, 10 to the minus 6 somewhere, 10 dB. Okay, 10 dB. So if you go like that, so 10 to the minus, okay, 6 is 10 dB. So, it's, I think L is 5 is almost approaching. 10 dB, 10 to the minus 6, we are almost here as well. Yeah, we are here. Yeah, so. Any other question? So this is time diversity is the one I show you so far. Next, I'm going to move to the antenna diversity. So that's the interesting part, okay? So antenna diversity mean you send the information through, again, independently faded path, but by doing different antennas, okay? So this one is called receiver diversity. So you have 2 antenna at that receiver. So let's consider base station here. For 4G base station, or 3G base station, we used to have a 2 antenna. So here is a 2 antenna. Let's say 2 antenna, and let's say your mobile phone, okay, have 1 antenna. Okay, your mobile phone have 1 antenna. So you send the information from uplink information. It goes from 1 antenna to 2 antenna. This is called single input, multiple output case, SIMO channel. Okay, so in this case, your information that you send, you go through different independently faded channel H1 and H2. Okay, so this is the example receiver diversity. Okay, receiver diversity. As I said, your 3G base station have used to have 2 antennas. In that case, uplink information is sent. You will get receiver diversity. Okay, so this is the SIMO channel, single input, multiple output. And let's say same thing. Now the base station is sending information to user. Okay, the base station now have a 2 antenna sending information to here. So this is multiple input but single output, MISO channel. This is called transmit diversity. Multiple input, single receiver. Okay, here single input, multiple output. Okay, CMOS channel, MISO channel, and you know, this, let's consider your Wi-Fi router have a multiple antenna. Your laptop also have a multiple antenna. This is both transmit and receiver diversity. This is the one, the MIMO channel. Okay, so this will be, your information will go through differently independent fader channel. You get space diversity or antenna diversity. Okay, so let's talk about receiver diversity. Okay, so receiver diversity. So so how do we get this equation? So you have one antenna here. The channel is H1 here. The channel is H2 here. This is single input, multiple output channel. So your receive signal here, let's say Y1 is H1. You transmit X here. So X plus noise W1 at the receiver. And you have a Y2 here, go through the channel H2, X plus W2. And you put this as a vector now, Y1 and Y2 as a vector, and you have a vector channel H1 and H2 into X, W1, W2. So this is the one written as a HX plus W. Okay, so that's the equation is written here. So this is the vector now, H is a vector and the W is a vector. Okay, so what we will do is, we assume receiver know the channel. We need to estimate the transmitted signal, which is X. What you do is a maximum ratio combining or match filter. How do you do that? You multiply the sufficient statistics to detect X is you multiply the received signal by its channel complex conjugate and divided by H. So this is called, this is a sufficient statistics to estimate X. Okay, so this is called match filter, maximum ratio combining, and there's another name, receiver beamforming. All are same thing. Okay, so in the book, people say match filter, and they say maximum ratio combining, coherent combining, and receiver beamforming. Everything is the same thing. You multiply the received signal by channel complex conjugate and divided by its magnitude. So this guy is a sufficient statistics to estimate X. Okay, so these have a different name. So this is the receiver beamforming. Receiver beamforming. Receiver know the channel and is multiplied by its conjugate and divided by magnitude, and you will be able to estimate X. So transmit beamforming. So let's say you have a now we are talking about transmit beamforming or transmit diversity. So we have a multiple input, single output channel. So you have a 2 transmit antenna and single receive antenna. So this is you consider as a 3G downlink transmission. So this guy need to send some information, let's say X. It's do a transmit beamforming. It's similar to is multiplied by not conjugate, divided by this. This is and this is going to be a vector now. X1 goes through this one, X2 go through this one. Okay, so this is a small x, and this is X1, and this is X2. Okay, so you multiply the x by the channel. Here, transmit beamforming, we assume the channel is known at the transmitter. So how do we assume that, let's say you have a base station here, have a 2 antenna. You have a user, have a 1 antenna. Okay. So how the user know the channel between here to here? This guy will send the pilot signal, and from the receive signal, this guy can estimate the channel coefficient H1 and H2. So the receiver, so similarly, if it is uplink, this guy will send the pilot signal. From the pilot signal, the base station will estimate the channel. So receiver knows the channel is a good reasonable assumption. Okay, receiver know the channel is a reasonable assumption. That's what happened. That's called coherent detection. That's what happened in 3G, 4G, 5G. Okay, everything is receiver know the channel. But if you assume transmitter also know the channel, it is something more stronger assumption. How do we know the transmitter know the channel? So this guy send the information, pilot information, and this guy estimate the channel, and then it will feedback the channel to the base station. So this guy had to estimate the channel and had to feedback. So it involved more resources. He had to feedback the channel. So transmitter know the channel is some very strong assumption. Okay, but I'll talk later on. There are two modes of transmission. One is called TDD, time division duplexing. Other one is called FDD, frequency division duplexing. The frequency division duplexing, we need to do a channel feedback, estimate the channel, and you need to send it back. So, so FDD mode of transmission need channel feedback as well. So this is this consume lot of resources. You need to estimate the channel and you need to feedback. For in the case of 5G, okay, 5G we have a massive number of antennas here at the base station, and this guy estimate the channel between all the antennas to his own receiver, and feedback it is a lot of resources. Okay, so that's why in 5G all the base stations are operating at TDD mode, not FDD mode. But up to 4G, the mode of operation is mainly FDD mode, because the channel estimation and feedback is not that strong wastage of resources. So FDD mode of operation was, I'll tell you later on, FDD mean the uplink and downlink communications are different frequency. TD mean time division duplexing and downlink are the same frequency. Okay, if it is same frequency, there is a channel reciprocity is there. So TDD is a good mode of operation for the MIMO case. Anyway, so I'll tell you all these stories later on, maybe tomorrow morning. So now the message is transmitter know the channel is a very strong assumption. But to do a beamforming, we need to know the channel. Because we need information is X, you need to multiply by channel and divide by its magnitude. So this is called transmitter beamforming. To do that, you need to know this channel. Okay, so this guy need to estimate the channel, had to feedback to transmitter, then only this guy can do a transmit beamforming. Okay, so transmit diversity, if the transmitter know the channel, it will send this information like this, and then the receive signal, normally we write H Hermitian into X and plus W, and this H Hermitian is here. X is this guy, this is the H X, and let's say this is a capital X here, this is a capital X, let's say, into small x. So you will get H magnitude small x plus W. So now you will get the same equation as before to detect. So this is the way the transmit beamforming is happening. Okay. So here also maximize the receive SNR by in-phase addition of the signal at the receiver. So this is called transmit beamforming. This is called transmit beamforming. Okay, so it's reduced to scalar channel. This reduced to scalar channel here. So same as the receiver beam. This is the same as the receiver beamforming. Receiver beamforming also we get the same equation. So it's not here. You will get the same equation. Okay, so these are the transmit diversity and receiver diversity. So let's see if transmitter does not know the channel, what happened? What happened if the transmitter does not know the channel? If the transmitter does not know the channel, mean it cannot do a transmit beamforming. Transmit beamforming, it had to multiply by the edge and divide by its magnitude. It cannot do that. So in that case, in early 19, somebody called Alamuthi, okay, Suwas Alamuthi, he was working at AT&T Wireless in the west coast of USA. He come up with the techniques called space-time code, okay. So that if you use that space-time code, then you will get diversity, but you don't need to know the channel, okay. So that's called space-time block code, okay. So this is very popular in early 90s because the 3G base station normally have a 2 antenna, okay. A base station have a 2 antenna, and it can do a space-time block code transmission to downlink users, okay. So I will maybe explain about the space-time block code after the break. Yeah, we'll take, yeah, okay. Yeah, yeah, okay. Okay, so we saw in the last class, for the multiple input, single output case, there are two channel coefficient H1, H2, and if the channel is known at the transmitter, you do a transmit beamforming, and X is the information that you need to transmit. You multiply the X by H and its magnitude, then we can show the receive signal Y. We normally write this way, and this is H Hermitian, and this guy is this guy, and this mean, and it will boil down to X plus W. So this is the transmit beamforming that we saw it, okay? So in order to do transmit beamforming, you need to multiply the transmitted signal by h divided by h magnitude of that guy. This is the vector channel, okay? So h here is h1, h2, okay? So this is the transmit beamforming. In order to do that, you need to know the channel at the transmitter, okay? So, but what happens if you don't know the channel? Then there is a person called Alamuthi, Sivas Alamuthi. He was in AT&T Wireless in the early 90s. And he come up with the techniques. As I said, transmitter know the channel is a big assumption, okay, big asking. So he come up with the techniques called space-time block code. Okay, it's very popular in the 3G era. You know, when the base station normally have a 2 antenna and doing downlink transmission is done using space-time block code. So he come up with the space-time block code. This is going to achieve this. I'm going to tell you what is space-time block code in a minute. That space-time block code is going to achieve diversity, okay, without knowing the channel. So what is his techniques is, so you have a 2 antenna here, again a MISO channel, 1 antenna receive, and you transmit U1 here at first antenna, you transmit U2 at the second antenna at time 1, okay, at time 1. Then what you do is you transmit minus U2 conjugate at time 2 and U1 conjugate at time 2, and then you arrange the receive signal. So there is a receive signal Y1 at time 1, and then receive signal Y2 at time 2. So let's say this is a H1, and this is, let's say, H2. Okay, so time 1, at time 1 is going to be H1 U1 plus H2 U2 and plus noise. Okay, at time 2 is going to be H1 minus U2 conjugate and H2 U1 conjugate and plus noise 1 here at time 1 and noise 2 at time 2. So then, so this is called space-time block code, okay? Space-time block code, okay? You transmit 2 symbol at 2 time, but the second time when you send, you do something, you know, conjugate, etc., like this, okay? So this is called space-time block code. Then you can arrange this receive signal Y1 and Y2 in such a way, okay? You can rearrange these 2 equations that I wrote here. You can rearrange this equation like this in the first line here, and then you can also take a conjugate of the receive signal here, and you can put as a vector here. It will be you can write like this, okay? The same equation you can rearrange. You take a conjugate of this receive signal and you can arrange like this. So what is you are seeing here? You know, once you do that, this column and this column are orthogonal now. This column and this column are orthogonal. If you take this column into this column product, it is going to be 0. These 2 columns are orthogonal. So that's what he did it. So by doing this conjugate and minus, etc., it turned out to be these 2 columns are now orthogonal, okay? Then by projecting the 2 column of the H matrix, this is the capital S matrix, you can decouple this equation like this, okay? Now you have a, you know, R1 H X1 U1 actually, U1 some noise, and you can write R2 H U2 plus W2, okay, U1 W2. So you can, by doing this projection, like a maximum ratio combining, you will be able to write this equation like this, okay? By doing so, you can see now the U1 information, the information U1 and U2 is going through two channels because H is a vector here. It is going through both channel U1 and H1 and H2, and you will get diversity. So that's the Alamuthi scheme. Alamuthi scheme is just this scheme. You know, you transmit U1 at the first antenna, U2 to the second antenna. The second time slot you transmit U2 conjugate and minus, and U1 conjugate, etc. By doing so, and you can rearrange the signal like this. Now this column into this column are orthogonal. And by doing projection, and you will get this equation. So the U1 go through this vector channel, so you both H1 and H2, you get diversity, and U2 also going through decouple and go through H1 and H2, and you get diversity. So we will do some question on how do we get diversity, etc. in the some of the tutorial question in the afternoon. So here, you know, we are not repeating. We are, you know, even though it's a 2 time slot we are using, but we are sending 2 information. So it is still, you know, better than the repetition code. Okay, repetition code, what you do is you send same information again and again, but here we are in the 2 time slot, we are sending 2 information, U1 and U2. And one thing is here, compared to transmit beamforming, this guy will have a 3 dB loss in SNR, okay? Because transmitter know the channel, you can do a transmit beamforming, you will be able to get a you know, coherent combined receive signal that will give you 3 dB gain compared to here. Here we are not doing the coherent combining, so there is a 3 dB loss of receive SNR compared to transmit beamforming. Okay, so beamform, if the transmitter know the channel, you can do transmit beamforming. That will give you some SNR gain, but space-time block code, we don't know the transmitter. Space-time block code, we don't know the channel, so there is a 3 dB loss compared to this guy. Any question about space-time block code? So this, so the 3G downlink, we are using space-time block code. So he become very popular, that guy, Alamuthi. He came to UK and he become a Vodafone CEO for some time in UK, and now he went back to America as well now. So anyway, he was very popular in the 3G era. So then, how do we do space-time block code for more antennas? This is only for 2 antennas. If we have 4 antennas, but how do you do space-time block code? There are so much research happened in 1990 to 2000 and even 2010. There are so much research. People are trying to do the space-time block code for more than 2 antenna, 4 antenna, 8 antenna, etc. Yeah, you can extend to 4 antenna, but things are become complicated. So there are some results, space-time block code design. So this is the space-time block code. Some people derive a lot of results after that. So this is the space-time block code. So this xi that I'm U2 conjugate minus U1 and U1 conjugate U2. This is called a space-time block code matrix. Okay. A space-time code is a set of matrix. This set of matrix. So this results is for general, space-time block code kind of scenarios. Okay, space-time block code is a set of matrix xi. Full diversity is achieved if all pairwise difference have a full rank. So then people come up with a lot of theory behind these things, and they're saying the full diversity is achieved if the pair of different matrices are full rank. The coding gain is determined by the determinant of this matrix here. So there are a lot of results have been derived after this space-time block code came, okay, and then generalized to more antennas, etc., etc. So transmit diversity codes have a okay. So it is saying. So if you have a time diversity code, like a turbo code, etc., we can put a space-time block code like diagonal matrix, and then the determinant reduced to a product of a square product of the diagonal elements. Anyway, so that's all I wanted to say about space-time block code. But we will have some tutorial question on space-time block code later on. So I send you the slides and you forwarded to the students, huh?
Yeah, I said I forwarded to everyone.
Okay. So the yesterday's slides you received already. One of the thing is for tutorial questions, yeah? Yes. Yeah. So in that tutorial, we have some question on how to design space-time block code, etc., and the performance analysis, etc. We will do some question in the afternoon. You will understand more about by doing so, how do we get diversity 2 or more, etc. Okay. So now I'm going to move to kind of a MIMO case. So MIMO, spatial multiplexing, capacity, multiplexing architecture, and pre-coding. So this is the very important stuff. Hopefully I will talk tomorrow as well. This is the foundation lead to 4G and 5G as well. Okay, so until 3G, we were using CMO or MISO kind of a channel. We didn't use the full MIMO channel, multiple transmit and multiple receive. And 4G onwards, it become MIMO and messy MIMO architectures are deployed. Okay, so the next slide set of slides is going to talk about MIMO, spatial multiplexing, capacity, multiplexing architecture, and pre-coder. So the main story, we start with the okay, I already talked about that. We start with single input, multiple output, and multiple input, single output channel. They provide diversity, and they also provide power gain, but they don't provide a degree of freedom gain. So I will tell you what is the degree of freedom gain later on. So the MISO and CMO channel, if you do a receiver beamforming or transmitter beamforming, it will give you a power gain and also give you a diversity gain, but it won't give you another gain called degree of freedom gain, okay, or spatial multiplexing gain. I will tell you about what does that mean. The MIMO channel is going to give you a degree of freedom gain and the spatial multiplexing gain. Okay, degree of freedom gain is most usual in high SNR regime. As I said, we always talk about high SNR and low SNR. So those things, so in the degree of freedom is very prominent in the high SNR regime. Okay, MIMO channel have a potential to provide a degree of freedom gain, and so I will show you about that, and then I'll talk about capacity of the MIMO fading channel, nature of the gain. Okay, we have both degree of freedom gain and the power gain. Then I will talk about transceiver architecture for fast fading channel for the MIMO case. That's called VBLAS, Vertical Bell Laboratory Layered Space-Time Architecture. Then I'll talk about transceiver architecture for the slow fading channel. That's called DBLAS, Diagonal Bell Laboratory Layered Space-Time Architecture. Hopefully, tomorrow morning I'll talk about multi-some MIMO downlink pre-coding techniques. Then that will lead to my MIMO stuff as well. So that's the plan for today, rest of the today and tomorrow. So we already seen this one, transmit, this is the CMO channel or receiver beamform, receiver diversity. This is a MISO channel, transmit diversity. This is both transmit and receiver diversity. We saw this one already. So now I'm going to talk about this MIMO channel. So MIMO channel here, let's say 2 transmit and 2 receive antenna. So this channel coefficient we normally write H11, and this coefficient we write H22. There's a channel coefficient here, we write H21. Here we write H12. Okay, so let's say you transmit X1 here and you transmit X2 here, and your receive signal here Y1 is X1 into H11, so H11 into X1, and then X2 into this channel, H1 to X2, and some noise W1. Okay, so, and Y2, the receive signal at this point, antenna came from the first transmit antenna and the second transmit antenna. So H21 into X1 and H22, this channel into X2 and W2. So now you put this receive signal Y1 and Y2 as a vector here, and you will get H11, H12, H21, H22, X1, X2 plus W1 and W2. Okay, so the vector receive signal can be written as the matrix channel into transmit signal plus noise. So this is the MIMO receive signal model. Okay, so that's the equation written here. Y is the vector, is normally, if you have a, let's say if you have a, people say NT transmit antenna, and let's say people normally denote NR receive antenna, your receive signal Y, which is NR into 1 vector, into H, which is NR into NT matrix, X, this is vector again, this dimension is NT into 1 and plus noise. Okay, so this is the general equation. Okay, if you have a NT transmit antenna, NR receive antenna, the receive vector NR into 1 vector is written as matrix NR into NT matrix, and X transmit signal vector NT into 1 vector, and W is NR into 1. So this is the general receive signal for NR NT transmit antenna and NR receive antenna. Anyway, so this one is for the 2 transmit antenna, 2 receive antenna. This is the way you write receive signal. So here H is the NR by NT fixed channel matrix. Okay, H is the NR, number of receive antenna into number of receive transmit antenna. So now, once you put all these things in a matrix form, we have a beautiful linear algebra theory can be used to derive many results. Okay, so we will see some of them maybe today. So once we have a matrix channel, we can do a lot of linear algebra techniques. Okay, so one of them is called singular value decomposition. So we can do a singular value decomposition of the channel matrix, like a U lambda into B complex conjugate Hermitian. Okay, so U and B are complex orthonormal matrix, and lambda is a real diagonal matrix contain singular values. I hope you know singular value decomposition. In MATLAB, you can write SVD into H, it will give you a singular value decomposition. You can put U, V, lambda. In MATLAB, if you do, you will get singular value decomposition. How do we get eigenvalue decomposition in MATLAB? You do EIG, H, and you will get eigenvalue decomposition, okay? E and the lambda, eigenvectors and eigenvalues, etc. Anyway, so if you do a singular value decomposition like this, so your receive signal, let's say this is the equation 1, okay? I'm multiplying this equation 1 into U Hermitian. What I'm going to get is, okay, U Hermitian into Y and U Hermitian into H. H is that singular value decomposition. U lambda V Hermitian into X. Okay, so here in the book we wrote like a star. It's not a complex conjugate. It's a Hermitian transpose. Okay, so I'm writing Hermitian transpose like a H here. Okay, and then okay, so you will get this equation. So what I did is I multiply this equation by U Hermitian, and U Hermitian into Y, U Hermitian. H is your SVD. This is the HVD, singular value decomposition. I get this. Okay. Now I denote this guy as a tilde. Okay, Y tilde. And U Hermitian into U, they are orthonormal matrix. This become identity. These guys are identity. Okay, so now I get lambda, and this guy, I denote X tilde, then I get X tilde, and I'm denoting this guy as a W tilde, so this becomes W tilde. So now what happened is, this matrix channel have a, you know, full matrix. It's now turned out to be parallel channel. Did you get what I'm saying is, so you have Y1 tilde, Y2 tilde, etc. Okay, is equal to lambda 1, lambda 2, these are singular value, up to lambda, let's say, n min 0, 0, and you have a x1 tilde and x, you know, tilde and some noise. Okay. So what I did is by doing this SVD decomposition, etc., I changed the matrix channel as a, this is kind of a scalar channel. You can see the yi tilde is lambda I xi tilde and some noise. Okay, so this is like a scalar channel now, scalar parallel channel. This is a scalar parallel channel. Now we can write the capacity and everything easily. So by doing, so that's why the matrix, once you put a matrix channel receive signal, then the beautiful linear algebra theory can be applied, and you can get a lot of insight about the capacity, diversity, degree of freedom, gain, etc. Okay, so that's what is shown here. So this one is showing between x tilde and y tilde, there is a parallel channel. Okay, if you see y tilde is here, this is the y tilde, and this is the x tilde. You do all these U Hermitian, etc., etc. You can see this is considered as a spatial parallel channel. Okay, spatial parallel channel, because the off diagonal terms are now 0. Okay, off diagonal terms are 0. So capacity is achieved by water filling over eigenmode of H. Okay. Anybody heard about water filling before? Yeah, water filling. Okay. Okay, so water filling is not coming here, but I'll tell you later on. So, so this all these things are shown in this diagram. So look at the Y tilde, this guy, and the input is X tilde, and you can see these are now changed to spatial parallel channel. Okay, so this there's a n min term here. What is this n min term is? N min is minimum of nt comma nr. Okay, so this is called n min. Okay, minimum of nt comma nr. In this case is 2 because true transmitter and true receiver. So n min is 2, but you can have 4 receive antenna, 2 transmit antenna. In this case n min is 2. You can get different values here. So this guy, I will tell you later on, this guy is called degree of freedom gain, or also called multiplexing gain, this n min. Okay? So your capacity is linearly increased with n min. So if you have a more antennas at the transmitter and receiver, the n min is the one will give you a capacity boost. Okay? So this is called degree of freedom gain. So this one is not exist in the CMOS channel or MISO channel because it's always 1. Okay? In the CMOS channel or MISO channel, or the transmitter antenna 1 or receiver antenna 1, so n min is 1. But the MIMO case, this n min is more than 1, it will give you a degree of freedom gain or multiplexing gain. So that's the one I mentioned before. The MIMO will give you a degree of freedom gain. Okay? That's one thing here is saying capacity is achieved by water filling over the eigenmodes of H. Maybe we will do a question how to do water filling later on, but for the time being, leave it. Okay? Maybe I can explain as well. So what is this water filling is saying is the capacity now is we'll come back. We will come back to that. So as I said, the linear algebra theory now play a big insight of our MIMO channel. So the rank and the condition number, you may heard about these things. These are linear algebra terms, rank of the matrix, the condition number of the matrix. These all are linear algebra stuff. It is coming here to show, if you have a full rank matrix, what is the, benefit if it is the condition number is if you have a well-conditioned channel matrix, you get more capacity. If you get an ill-conditioned matrix, you won't get the capacity much, etc. Okay, so high SNR. So there's one thing I'll tell you later on about the water filling. Okay, water filling mean you have a power here, transmit power. You allocate that power according to the channel, the eigenmode. Eigenmode are the lambdas. Eigenmode are the lambdas. You allocate the power according to this eigenmode. But if you have a larger number of high power, you don't, it's called high power mean high SNR. You don't do power allocation. You do equal power allocation. So that's what it says here. High SNR, equal power allocation is optimum. Equal power allocation mean you have a P power, let's say total power is P. You divided, there are NT transmitter antenna, so you spend power here P over NT, okay? You divided by equally to each of these antenna, so that's called equal power allocation. Okay, so that's what it's saying. Equal power allocation is optimum in high SNR. The capacity can be written as this form. So how do we get that capacity? Capacity is 1 plus SNR. Okay, so SNR is this guy is SNR. Okay, so 1 plus SNR. There are n min channels are there actually. Okay, there are n min channel. Is over there. I say K here. So there are n min channel. So the capacity is a summation of these parallel channel. So that's why there is a summation coming here. So, okay, so this is the capacity, okay. So this can be written as at high SNR, as I said, wireless communication, we talk about high SNR, low SNR very often. High SNR, what you do is we can, this guy is very big, this guy is very big. This is SNR, it's big compared to 1, you ignore this guy, okay. So if you ignore this guy, you can write like this, okay. So your capacity formula is going to be summation of I is equal to 1 to, let's say, n min, okay, log 1 plus p over, I'll keep a k here, p over k, the power allocation, and lambda I squared is the gain of this channel, and divide by n naught, okay. So high SNR is approximation. High SNR approximation means you ignore this 1. So what you do is equation is going to come like 1 over k log p over k lambda I squared over n naught. This is the approximation. You know high SNR. This guy is very big compared to 1, so you can ignore the 1. You can write like this. Now the log 2 term are there. So you can write this as a, you can write like p over n naught as a SNR. So you can write, k into log SNR. So what I did is p over n naught as a SNR. There are summation 1 to k, so k into SNR, and you can write a remaining term as a summation log lambda I squared over k. So you can write like this. So that's what is written here. Okay, so as soon as you ignore this 1, you have a 2 term. So log product can be written as a summation, and you can write like this. So that's what is written there. K is the number of non-zero singular values. Okay, so what is the, here, lambda I is a singular value of H matrix, okay? What is lambda I squared? Lambda I squared is a eigenvalue of this guy, okay? So I hope you get this one. Lambda I is the singular value of H matrix, but lambda I squared is an eigenvalue of this matrix, okay? Anyway, so the next thing is called condition number. The condition number of the matrix is defined by maximum lambda I over minimum lambda I. If this guy, condition number, is very close to 1, then your matrix is very, good condition, okay? And then, in other words, the maximum lambda I over minimum lambda I is 1 mean your maximum singular value and minimum singular value of the matrix is almost same. That's why it's become 1. Then you will get a high capacity. So you have all the eigenmodes or the lambda i's are good, equal value, you get lot of high capacity of the channel, okay? But if you have a channel matrix have a ill condition, in that case, your minimum eigenvalues are very, very small compared to maximum eigenvalues, okay? So you put maximum, or these guys are very small. If the matrix is ill condition, then this condition number become very large, and that case, you won't get capacity, okay? So, so in order to get high capacity, your channel here had to have a rich scattering, okay? Between transmitter and receiver, your channel had to be a rich scattering. If you have a rich scattering in between transmitter and receiver, your H matrix going to have a good condition number. Good condition number, you will get capacity. If it is a don't have a rich scattering, this guy is going to get a, you know, ill-conditioned matrix, and you won't get that much capacity. So rich scattering means a lot of scattering had to happen transmitter receiver. If the transmitter receiver is very close together, you have a line of sight environment. So then this guy is not going to be full rank, and it's also going to have a ill condition, and you won't get high capacity. So this is the beauty of linear algebra theory application to channel capacity formulas. Okay. Any question? Okay, so transmitter receiver CSI. CSI mean channel state information. CSI mean channel state information. Okay, so this slide is saying transmitter and receiver CSI. So transmitter also know the channel. Okay, transmitter receiver CSI mean this channel is known at the transmitter and the receiver as well. Then only you can do this kind of you can multiply the transmit signal by V Hermitian and etc. Okay, so that's what this slide is saying about. If the transmitter and receiver know the channel state information CSI, we can decompose the MIMO channel into bunch of orthogonal subchannels. That's what we did, and then each of these subchannel we can send independently faded, independently coded signal. We can do any GIAN code. We can do a turbo code here and send through one of the eigenmode. You can do another stream, another turbo code, and send through the another eigenmode, etc. And it is going to be min of nt comma nr. So if you have a lot of transmitter NR compared to receiver NR, some of the transmitter NR you won't be able to send information. Okay, so that's what this slide is talking about. So you can send each of these eigenmode independently coded stream. Okay. In order to do that, you need to know the transmitter, know the channel. Then only you can multiply by V Hermitian here. You do a pre-processing here. We multiply by channel information. Okay, as one of the SVD matrix here. So in order to do that, you need to know the channel at the transmitter. And the receiver, you multiply by U Hermitian here. Okay, so the next slide is showing this is very similar to OFDM. Okay, I hope you know what is OFDM is. In OFDM also, this is an analogy with OFDM. OFDM also, we do a inverse Fourier transform at the transmitter and discrete Fourier transform at the receiver. Okay, so here also, you are multiplying by V at the transmitter, you are multiplying by U at the receiver. So these are very similar, the MIMO case and the OFDM. OFDM, this is application to a single input, single output system, but you do inverse discrete Fourier transform at the transmitter and discrete Fourier transform at the receiver. So this slide is saying there is an analogy between OFDM and the MIMO channel. Okay, so but there is a major difference. In MIMO, we multiply U and V matrices. That depends on the channel. But in OFDM, you multiply by the inverse discrete Fourier transform and discrete Fourier transform. They are not depends on the channel. Okay, in OFDM, the inverse Fourier transform and the discrete Fourier transform matrices do not depend on the channel. So that's one message in this slide. Any question? Okay. So let me continue. The channel receiver CSI only. Okay. As I said, receiver know the channel is the good assumption. Okay. Receiver know the channel all the time. Your 3G, 4G, 5G phone always estimate, receiver always estimate the channel. Okay. Base station estimate the channel for each of the coherent time. Your mobile phone estimate the channel each of the coherent time as well. So this is the kind of a reasonable assumption, but transmitted on the channel is a little bit more, okay? But 4G base station, assume transmitter know the channel in order to do pre-coding, which I will talk tomorrow in the FDD mode. Okay, channel matrix H and its singular value lambda i's are random and unknown to the transmitter. So, okay, yeah, so now the transmitter does not know the channel, so they cannot multiply the transmitted signal by the one of the, SVD matrix V. So they cannot do that because transmitter does not know the channel. So in that case, this matrix is going to be just an identity matrix. So it's like Q become identity matrix because transmitter does not know the channel. So if the transmitter does not know the channel, it cannot do a power allocation, like a water filling power allocation, etc. Then in that case, it do equal power allocation like this, okay? Okay, so what it's saying is channel matrix H and the singular value lambda I squared are random and unknown to the transmitter, has to fix Q and power allocation independent of H, and it's normally do a uniform power allocation is optimum in many cases. So in this case, it cannot do any pre-coding or anything, so just do identity matrix here. So it turned out to be uniform power allocation is optimum if the receiver transmitter does not know the channel. It is not trivial to come up with the capacity achieving architecture if we don't know the channel at the transmitter. So, so now we talk about capacity. So we have already wrote the capacity formula here for the MIMO system. The MIMO system capacity can be written as this formula because there are n parallel channel. N mean parallel channel, so there is a capacity formula, this one. Each of these capacity of the parallel channel are add together, okay? This can be written as log determinant formula, okay? So now you see a lot of linear algebra is coming here. So what is the eigenvalue of this guy? So eigenvalue of this matrix. So eigenvalue of this matrix is actually 1 plus, this SNR over NT into lambda I squared. So this is the eigenvalue of this matrix, okay? So determinant of this matrix, let's say this is alpha. So determinant of this matrix, det of that matrix, is going to be product of eigenvalues lambda I, okay? So log product is become summation, okay? So this is I hope you understand this. So eigenvalue of this matrix, identity matrix plus SNRNT over H into H Hermitian. I told you this lambda, we start with this lambda as a SVD, singular value of H matrix. But lambda I squared is the eigenvalue of H into H Hermitian matrix, okay? So this lambda squared now, which is the eigenvalue of this matrix, H into H Hermitian matrix, H into H Hermitian matrix. So this is the eigenvalues, okay? Anyway, so the eigenvalue of all these matrix are 1 plus P over NT lambda I squared over N naught. So determinant of matrix is the product of eigenvalue. And product of eigenvalue, in front of that you have log, so it's log product is written as summation. So that's the formula for the first equation. I hope you got it, okay? So I'll repeat again. H have a singular value lambda, but lambda squared is the eigenvalue of H into H Hermitian, okay? And this matrix have an eigenvalue, these guys are eigenvalues. And determinant of this matrix is product of eigenvalues. So this is, you can write as a product of eigenvalue, let's say lambda alpha. So product of, then you take a log in product and it can be written as a sum, okay? So this is, I hope that you understand. So MIMO capacity is log determinant I plus SNR over NT, H into H Hermitian. So this is the channel capacity formula for MIMO case. So anyway, in this case, okay, so there are two capacity we normally define. H is a channel between transmitter and receiver. This H is the channel is a random variable, okay? Channel is a random variable. I told you channel will take a random realization and stay constant for particular time and take another random realization, stay constant for particular coherent time and take another random realization, et cetera, et cetera. So this guy is random, this guy is random. So all these capacities are random. All these capacities are random. So random variable, if we take a mean of that random variable, if we take a mean of this guy, this is a random. The H is random, so determinant is random. In front of log is also random. So all these things are random variable. If we take a mean of that guy, this guy, this is called ergodic capacity or mean capacity. So you take a mean expectation of the same thing. So this is called, so we talk about two fading, fast fading and slow fading. In the fast fading case, the information theoretic measure is called ergodic capacity or mean capacity. So that what is mean capacity or ergodic capacity? It's an expectation of this random variable. That is the mean. So that's what fast fading is here, okay? So it's an expectation of this random variable. This is a single, this is, even though this guy is matrix, is when you take determinant, this becomes scalar. It's a scalar random variable, okay? This is the mean capacity. It's a mean of this random variable is this. So this is, if you are in the, talking about writing papers with the fast fading channel, your information theoretic measure is the mean capacity or ergodic capacity. But if you are talking about your channel as a slow fading channel, your information theoretic measure is outage probability and outage capacity. So what is outage capacity and outage probability mean? So you are given a slow fading channel, you assume that this channel can support rate R. You assume it's a slow fading channel, your coherent time is very large. You assume this channel can support R bits per second per hertz, something like that. And then you, according to that R rate, you do coding and everything, transmitter, receiver design, you transmit, okay? Whenever that channel become very bad or in the deep fade, it won't support that your rate R. In that case, you are in outage. So what is the probability you are in outage is called outage probability, okay? So if somebody gave you outage probability, so let's say you are working in Qualcomm or somewhere, so you are asked to design a communication system, and your manager saying, I will be happy my outage probability epsilon is 0.01. So what does that mean? You take 100 realization of the channel, one of the channel is outage, so outage probability is 0.01. If what is epsilon is 0.1 mean, outage probability is 0.1 mean, you take 10 realization of the channel, only one of the channel will be outage. So you are given an outage probability, this guy, you go and find this R according to this formula, that R is the outage capacity, okay? So the information theoretic measure in the slow fading channel is outage probability and outage capacity. Information theoretic measure for the fast fading channel is the ergodic capacity or mean capacity. Okay, so this is very important slide. Any question on that? Okay, so because of this log determinant formula, you will get huge capacity. I'll show you in a minute. Okay, so this is the you know, you talk about MIMO all the time. You heard about MIMO. The benefit of MIMO is shown in this slide. Okay, so you see here we are talking about fast fading channel, IID relay fading. IID relay fading means all these channel coefficients are independently distributed. IID. So IID, all of them are independently, okay, your channel H. Channel H is a made element Hij, okay? This is what is the dimension? This dimension is NR into NT. NR receiver antenna, NT transmitter antenna. your Hij are complex normal, 0 mean, variant 1, okay? And they are independent. Each of these guys are independent, so we call IID relay fading channel. So that's the meaning, okay? You have a channel, all of these elements are complex normal, 0 mean 1, and they are all independent. Then this channel is called IID relay fading channel, okay? So let's look at the capacity, bits per second per hertz. So what is the maximum rate you can transmit? Reliably, it's the capacity, bits per second per hertz. This is SNR, okay? This is SNR. There are 3 curves are here. Let's look at this one, this guy, the red dotted curve. Oh, that curve is for 1 transmit antenna and 1 receive antenna. NT is equal to 1, NR is equal to 1, okay? Your capacity. Let's look at SNR is equal to 2 dB, so 20 dB. SNR is equal to 20 dB. What is the capacity you are getting? You go here, you are getting 5 bits per second per hertz, okay? 20 dB, you go here, and you go here, you are getting 5 bits per second, okay? This is a CISO case, single input, single output case. Same here, this one is for MIMO case, 4 transmit antenna and 4 receive antenna. So your power is same, 20 dB. You go here and you get 20 bits per second per hertz. So your capacity increased by 4 times, okay? CISO case, single input, single output case, your capacity is 5 bits per second per hertz. For the MIMO case, same 20 dB, you didn't increase the power. Even though you are putting more transmit antenna, but your transmit power is same for single antenna case, and some transmit power is same for the MIMO case as well. You are getting 20 bits per second. That's the beauty of MIMO. So you never increase, you put more antenna, but you never increase the power. Your capacity increase 4 times. What does that 4 come from? That 4 is actually min of 4 transmit NT, NR. So this is the multiplexing gain. In this case, transmit antenna is 4, receive antenna is 4, so the min, this is 4 times. So that's why 4 into 5 is 20, okay? You get, so you see that the beauty of MIMO is giving us a 4-time improvement, even though you are talking SNR is the same SNR for CISO case, MISO case. And there's another plot here, the blue one. This is a CMO channel, single input, multiple output channel, CMO channel. You will get some gain here compared to CISO gain. That gain is not spatial multiplexing gain. This gain is because you will get a little bit more capacity. This is not due to spatial multiplexing gain or degree of freedom gain. This is due to the receiver beamforming, the power gain that you are getting here. That's why you are getting a little bit more, okay? So yeah, this is the beauty of MIMO. Will give you more capacity. If you put more antennas, you will get more capacity. But when you put more antenna at the transmitter and receiver, you are not increasing the power. Power is same, but capacity is increasing. So here is again, the degree of freedom gain is min NT, NR. So this is the degree of freedom gain, min NT, NR, determine the highest and slope. I will tell you in a minute. So this is the plot same as the previous slide. This is the previous slide, 4 and transmit antenna, 4 receive antenna. I told you, you are getting a 20 bits per second, which is a 4 times compared to the CISO case. Now look at here, this is 8 transmit antenna, 8 receive antenna. Same 20 dB, you go here, you get 40. So 8 times 5, 8 into 5 is 40. So you get 8 multiplexing gain or degree of freedom gain. Now the min NT, NR, which is 8, and you are getting capacity improvement 8 times more. 5 into 8 is 40 bits per second per hertz. Okay, so this is the, this MIMO theory is the one that now you are enjoying, a larger capacity in your 4G and 5G phones because of this, okay? And 5G phones, we are talking about massive MIMO, So we don't talk about 8 antenna, 4 antenna. We talk about 64 antenna, 128 antenna. Even millimeter wave, you talk about 512 antennas, etc. So a lot of antennas will give you a lot of array gain, etc. So you don't, if you put more antennas, you are not putting more power in the transmitter, same power, but it will give you capacity improvement. Any question? Yeah.
Same multiplexing gain, you will get in both the cases of slow fading and fast fading.
Yes. Yeah. Yeah. You need to do, to get that, you need to do different transmission techniques. That's called V blast and D blast. Yes, I'll tell you in a minute, later on. Yes.
Basically, in any given system, is both the slow fading and fast fading scenarios exist in the same system?
Yeah, it depends, of course, yes. It depends on the scenario. So if you are, walking with the phone, it's a slow fading. If you are in the high-speed train, it's a fast fading channel, yeah.
So in the same system, it exists both slow fading scenario and fast fading.
It's, okay. It depends on the environment.
Automatically it will exist.
Yeah. So if it is a high-speed train, you are experiencing the fast fading channel. If you are walking, through and using the phone, your channel is slow fading channel. And slow fading and fast fading channels will have a different transmission techniques and all these things. Yeah. Okay, so that's one more thing. Saying high SNR slope. Okay, so this is the high SNR regime. Okay, this slope is give you a degree of freedom gain. Okay, so from this plot, you will see this slope is kind of 8, and this slope is 4. So that's what it's saying. The degree of freedom gain determine the high SNR slope. Similarly, if you have a bitter rate curve, if you have a bitter rate curve here, okay, it's like this, probability of error. The high SNR slope, this slope will give you the diversity order. Okay, the high SNR slope will give you the diversity order. In the capacity plot, the high SNR slope will give you a degree of freedom gain. Okay, so there are many insight you will see from the probability error curve and the capacity curve, etc. So there are many things are happening here. High SNR slope in the probability of error curve is giving you degree of freedom, diversity order. This is diversity order. Here it will give you a degree of freedom gain or spatial multiplexing gain. Any other question? Okay, so any other question? Well, I hope you are following with me. So now this is all high SNR. So let's talk about the low SNR case. Okay, so no, next one. Okay, this is a low SNR regime. So we talk about low SNR regime. Okay, so in CDMA. System operate at low SNR regime. Okay, anyway, we'll come in a minute. So this is a low SNR regime. This plot is showing MIMO and CMO case results. Okay, so you see here this. I hope you see this. The y-axis is capacity, normalized capacity divided by CISO capacity. Okay. So this one is for the blue curve is for the MIMO case, and this red curve is for the CMO case, single input, multiple output case, okay, CMO case. You can see at the low SNR regime, this is the low SNR regime. Why won't we are interested in low SNR regime? As I said, CDMA normally operate in the low SNR regime. In that case, MIMO and CMO are giving same performance. So then you ask the question, if I am using CDMA system, do I really want a MIMO system? The answer is mainly no. You don't need a MIMO system if you are operating at the low SNR regime. Even though in the point of view of capacity, you don't need a MIMO system if you are operating at the low SNR regime. Okay, but there are still MIMO will give you some another benefit of interference cancellation, etc. But capacity point of view, you are in the low SNR regime, you don't need a MIMO. So that's the message of this slide. So nature of the performance gain, high SNR, degree of freedom gain, which is a min NT, NR for of degree of freedom gain. MIMO is crucial. Okay, this gain is called degree of freedom gain or spatial multiplexing gain. At low SNR, NR fold power gain only need a multiple receiver NR. CMOS channel is good enough. Okay, you don't need a MIMO channel. At all SNR, this degree of freedom gain due to combination of both effect. Okay. So some questions are here. Should one blindly overlay MIMO technology on the CDMA universal reuse system? Because this CDMA system operate at low SNR regime, MIMO gain is mainly receive NR power gain. So that's what I said. You know, if you are operating at low SNR regime, you don't need a MIMO system. But having MIMO system, you can get some other benefit of canceling interference, etc. So which SNR that you are operating also very important thing to when you are designing a wireless communication system. So now we can talk about transceiver architecture. So this is called VBLAST, okay, vertical Bell Laboratory Layer Space Architecture. This is, this architecture is proposed in Bell Lab in New Jersey, early in 1990s to 2000 time. So this is called VBLAST architecture. This is for fast fading channel, okay? So can get a performance gain by sending independent. So this is kind of a surprising result. So okay, you send an independently coded stream through the MIMO channel. All these stream will interfere at the receiver, and you had to extract each of these stream at the receiver. Okay, so you need to do a clever signal processing at the receiver. Okay, so that's what it's saying. Can get a performance gain by sending independent coded stream on each of these transmit antenna, and you need to do a joint decoding here, because each of the antenna is sending a independently coded stream, okay, independently coded stream. So at the receiver, all the stream will be interfere each other, and you need a clever signal processing technique to extract each of the transmit stream. Okay, so that's it's called. This is surprising. Even though this independently stream interfere at the receiver, we can still decode all these independent stream and get the degree of freedom gain. How to get the degree of freedom even when the streams are interfere with each other. Okay, so these Bell Lab people come up with the BLAST architecture that can decode, okay, decode this stream independently and decode this stream in the independent coded stream and get the capacity. So you need a receiver here which is the one I'm going to talk later on. So the receiver here, you are sending an independent stream. Okay, you have a MIMO system here. Okay, you have a MIMO system here. NT transmit antenna. You have a receive antenna, NR receive antenna. Each of these guys are sending independent stream. Okay, okay. So you have a big video that you wanted to send. Let's say big video that you need to send. Okay, or image you need to send. You divide that stream like this, and this stream 1 will go through antenna 1, stream 2 go through antenna 2, etc., etc. All this stream will be coded independently through this antenna, this antenna, this antenna. Then at the receiver, let's say you have a rich scattering here, and you receive this each of these stream together, and you need to decode each of these stream back and put it back this way to get your video back. Okay, so you need a very high signal processing techniques here. So you can of course use some ML decoding, maximum likelihood decoder here, but that is very complex. So we need to come up with some receiver design here. So the story is that I'm going to tell you. The easy receiver is a zero forcing receiver, and it won't achieve the full capacity. Then I will talk about MMSC receiver. That is also not going to achieve the capacity. And then I will talk about MMSC with SIC, successive interference cancellation techniques. This is a nonlinear receiver. These are linear receivers. The ML receiver that we can use here achieve capacity, but that is a nonlinear receiver. It is also very complex to implement. Nobody implement maximum likelihood decoder receiver. So we had to go zero forcing or MMSC receiver. These are linear receivers that won't give you maximum capacity. So the channel capacity, log determinant formula, give you the maximum rate that you can transmit, but it won't tell you, Shannon won't tell us how to realize that capacity. Shannon didn't say that. Shannon said, this is the much capacity you can achieve. No, and he didn't say to us how to realize that. So similarly here, these receivers not going to achieve a channel capacity. But this guy, MMSC with SIG, will achieve the capacity. And that is the one, we will be studying. All these things we will be studying in the rest of the lectures. Any question? I think maybe we can continue this one next time. Yeah, we can discuss now. So we will be studying this receiver here, zero forcing receiver, and MMSC receiver, and zero forcing receiver. Did you heard about the word zero forcing receiver? This is called, there are many names for this one as well. Interference nulling, decorrelator, zero forcing receiver. There are 3 names here. And MMSC is a minimum mean square error receiver, and this one is minimum mean square error successive interference cancellation. That is the one achieve the capacity that we saw the log determinant formula. Anyway, any question?
Yeah, please ask questions. I mean, we should be able to understand, right, whether you are understanding or not.
Yeah.
Huh? Is understandable, huh? If you're having any doubts or if you don't understand anything, please ask questions.
Okay, here I have a question. Okay. Diversity is going to affect the bitter performance. Yes.
So indirectly, it is also impacting on the channel.
Capacity also. Yes. Yeah.
MIMO is providing
yeah, yes. Yeah.
So whether which like antenna diversity or receiver which diversity gives more?
Okay, in MIMO we have both transmit diversity, receiver diversity all together. Okay, we have both. Antenna diversity have a two thing. One is transmit diversity and receiver diversity.
Both will be playing major role in enhancing capacity.
In the MIMO system, yes. Sorry, anything? Yeah. Yeah, yeah. CISO capacity, you know that, okay? You are asking the CISO capacity. That's just, log 1 plus SNR. So this is the CISO capacity. So this is a log 1 plus SNR. In the MIMO case, you will get a determinant and summation will come here. So that's why you are getting a MIMO larger capacity. So did I answer your question? So CISO capacity is just log 1 plus SNR. Yeah? That's what your question? Yeah. If you have interference also in the environment, then your capacity formula, you had to use log 2 1 plus signature interference plus noise ratio. Okay, if there's an interference. SNR is signal power divided by the noise power. But if you have interference also, then you talk about SANR, signal to interference plus noise ratio, signal power divided by the noise power and plus the interference power. Yeah. CSI means channel state information. Okay, so CSI mean channel state information. Let's say CSI mean channel state information, and then another CSI mean channel state information. CSIR mean channel state information at the receiver. So the receiver know the full channel. Receiver know the full channel for particular coherent time. Receiver know the full channel H matrix. Then only it can do zero forcing, MMSC, etc. Because it need a channel knowledge. And CSI, CSIT mean channel state information at the transmitter. Transmitter also somehow know the channel, okay? Or the partial channel knowledge is known. Some part of the knowledge is known at the transmitter,
So it is giving information about the nature and behavior of the channel.
The full channel is known.
Yeah, the nature, how the channel behaves and everything is given by the CSI.
Yeah, CSI, yes. Yeah, yeah.
And most of the times we hear the word imperfect CSI.
Yeah. Imperfect mean you need to, okay, so how do we estimate the channel? Okay, when you, how do we estimate the channel is the transmitter will send you some pilot sequence. Okay, pilot sequence mean in the standard, 3GPP standard, there are pilot sequence available. So transmitter will send that pilot signal and the receiver knows what is transmitted. Receiver knows what is transmitted because of the pilot. Then based on that, receiver estimate the channel, okay? So during the training, receive signal, let's say this is NR into how many pilot, a long pilot you are sending, let's say T, and this is H into X, X is NT into that T pilot duration, so plus noise, and the receiver, of course, know the receive signal, and also know the transmitted pilot signal, and that it will estimate this one using least square techniques, okay, or zero forcing technique. It will estimate the channel estimation. So the channel estimation is the channel is actually estimated. So it's estimated channel. The estimated channel is actually a true channel plus some delta estimation error. So in reality, channels are estimated, it's not a true channel. So there is a uncertainty as well, which is called channel uncertainty delta. So you know, your phone and all these things are based on estimated channel. It's still working fine, but it's not a perfect channel. It's estimated channel. So always there is uncertainty, channel estimation uncertainty. It depends on the SNR and also. If you are very close to the base station and your SNR is good, you will estimate the channel accurately. If you are in the cell edge, your channel is, you know, SNR is low, your estimation will be uncertainty involved. That's why you are getting a bad quality estimation and drop codes and all these things. Yeah. So if you are doing performance analysis, you start with the perfect channel and then you introduce channel uncertainties, and you know, there will be some degradation in the performance due to channel estimation error.
And if you elaborate on water filling, you told at the end of this.
Yeah. Water filling, okay. So what water filling mean? So MIMO case, you plot versus y-axis, n node, this is lambda. Lambdas are your singular value decomposition values, okay? Then you plot 1 over lambda I. So it is going like this, okay? It's going to be like this. I'm just drawing randomly. You know, it's going like this, let's say. So your first lambda I, a node over lambda I is this one, and the second eigen mode is, second eigen singular value mode is, let's say, this one, third, fourth, fifth, sixth, etc. So you plot it like this, and then you consider your power as a water, okay? Your power as a water, you put your water inside, okay? So once you put the water inside, it is going to be, depends on how much water you have or how much power you have. It is, let's say it's going like this, okay? It's going like that. And then you allocate power for that eigen mode. This is the power allocation that you are going to allocate, okay? So if you have a good eigen mode, this is very good value. 1 over this value will be smaller, okay? So here, if you have a very good eigen mode, so this guy is very large, so 1 over is very small. So in that case, you allocate more power, okay? The water filling power allocation is you send more power to good channel and less power to bad channel, okay? So then only you will get capacity, okay? So in this case, lambda is very good. In this case, 1 over lambda is very small. You allocate more power, okay? So the power allocation P star I is defined as, power allocation P star I is defined as, this one is, let's say, mu. This mu is depends on how much power you have or how much water you have. If you have more power, this mu level is going up and down. So mu minus this one, n node over lambda I, this is the power allocation, okay? This is the power allocation. So this is the power allocation. This is the power allocation. How do we get that the equation? Mu minus this guy. This guy is n node over lambda I, and there is a plus sign here, okay? If it is positive, you allocate power. In this case, it's going to be negative. It's a bad channel. Don't put power, okay? The information theory is saying, if you have a bad channel, don't communicate, okay? So in this case, your power allocation is 0, okay? And this case also, your bad mode, and you don't allocate power. So information theory is saying, if you have a bad channel, don't communicate. But if you have a good channel, try to put more power and communicate. That's what information theory is saying. But in reality, fairness and all these things are there. You know, so if you have a bad channel, if somebody is in the cell H, he is having a bad channel. So information theory is saying don't transmit to him, okay? But for the fairness, we transmit as well, okay? But you know, information theory point of view, you know, sending to bad channel person is a wastage of resources, okay? So, but when you consider fairness, we need to serve that person as well. So that is kind of a not information theoretically optimum, but we still send some power to that guy to serve as well. So the power allocation is saying if you have a good channel, you put more power. If you have a bad channel, don't transmit. And according to, yeah, this is called water filling power allocation. Okay, you plot n node over lambda I, and your power as a water, you put this water into this vessel, and this is the power allocation. So this plus sign mean, this plus sign mean min x comma 0. Yeah, so if it is negative, you put 0. If it is plus, you will put that value. That's this. Yeah, so this, yeah. The information theory is there saying if it is good channel, you transmit more power, but if it is a bad channel, don't transmit. But fairness issue, when you consider even if the bad channel, we will send some power. But that is actually not optimum, yeah. CSI? C. Channel quality indicator is also telling about the channel between transmitter, the quality of the channel, okay? CSI mean is the full channel information. The CQI is another indicator, but it's not the exact channel is given. Okay, it's going to be a, if you have a good SNR, your CQI is a large value as well, yes. It's a proportional mapping. The water film power allocation, we here for the MIMO case, I explained, you can do OFDMS also, different sub, in that case, x-axis is going to be the subcarrier, and yeah, subcarriers. So whichever subcarrier have a good channel, we put more power. Whichever some subcarrier is bad channel, we put less power, etc. There are some questions. Yeah, we will do some questions then later on. Any other question? So you know, transmit diversity, if you do need to do transmit diversity, you should have a more transmit antenna, and you should also have a channel knowledge at the transmitter. Then only you can do transmit beamforming and get the transmit diversity. Yeah, receiver diversity, if you have a multiple receiver antenna, you will get receiver diversity automatically. So, okay, so one of the application I explained to you in the 3G scenarios, our base station normally have 2 antennas, and when you transmit to downlink user, it will do a transmit beamforming, and when user send information uplink, we use a receiver beamforming, also receiver diversity, okay? So we cannot get both because one of them have one antenna. Okay, in 4G also similar, but now we have massive MIMO, and it's have a little bit different effect, array gate. 5G phones are, you know, still you are using one antenna at the receiver, but because of the large number of antenna at the transmitter, we are getting the array gain. Or you are getting a pencil beam to you, and that lead to big array gain, less interference as well, okay? Less interference, so your signal to interference plus noise ratio is very good. So because of that, yes. But in the millimeter wave frequency, your phone have more antenna, 4 or 8 antenna possible, 5G phones. Any other question? Okay, we can take a break then, yeah?
Yeah, should I ask them to come at 2 o'clock, sir?
Yeah, 2 o'clock, yeah.
Yeah, please come here at 2 o'clock. Huh?
So in the second question, I'm reading the question first. So consider the Rayleigh fading channel H and verify probability of error is equal to expectation of Q in bracket square root of 2 mod of H square into SNR, which comes out to be half 1 minus square root SNR over 1 plus SNR. We have to prove this, okay? So, write this. So this is visible, right? So I am denoting SNR by gamma, okay? So this is what we have derived yesterday. And now we have to take the expectation for H. Okay? So, everybody know how to take the expectation, right? So, we have to take the expectation with respect to H. So yesterday we proved H is what? Rayleigh. And H square is what? Exponential. Exponentially distributed with parameter 1. Okay? So we can assume this as Q square root 2 x gamma into the PDF of x, which is exponentially distributed, that is e to the power minus x. What is the PDF of exponential distribution? If we have some variable exponentially distributed with parameter lambda, its PDF is given by lambda e to the power minus lambda x, where x is greater than or equal to 0. Okay? So lambda parameter here is 1. So we will have dx and its limits from 0 to infinity. Okay? Now we will expand this. We can write the expression for q also. So let's say this is x and s equals to 0 to infinity and y equals to square root 2x gamma to infinity e to the power minus y square divided by 2 divided by the square root of 2 pi into e to the power minus x dx. This is okay, right? I have just substituted the value of q function. Now, if we see here, x is going from 0 to infinity, okay, and y is going from some line to infinity, okay. So this is like a vertical strip. Okay. So where x is going from 0 to infinity and y goes from particular value to infinity. Okay. And this line is y equals to square root of 2x gamma. Okay. So what we want to do now, we want to change the order of integration. Okay. So instead of taking this y strip, we can take like this x strip. Okay. So this will change the limit of the integration. Okay. So what will we have? We will have, so this is x and this is y. So y will go from 0 to infinity. Y will go from 0 to infinity, and this x will go from 0 to up to this line, and x will go from 0 to this line, and this line is what? y square equals to 2x gamma. So x is equals to y square divided by 2 gamma. So y square divided by 2 gamma. Okay. And we will have same thing, y square divided by 2 into e to the power minus x dx and dy also, dy divided by square root of 2 pi. Okay. Now this y square, we can solve this. Okay. So we will write here so we will have this limit. So we will write here y equals to 0 to infinity e to the power minus y square divided by 2 divided by square root of 2 pi into dy and 0 to y square divided by 2 gamma e to the power minus x dx. So this is x. Okay. So we can solve this. This comes out to be e to the power minus x divided by minus 1, and we can put the limit here, y square divided by 2 gamma. Okay. So this comes out to be 0 to infinity e to the power minus y square divided by 2 divided by square root of 2 pi, and this is if we put 0 minus e to the power minus y square divided by 2 gamma minus minus plus is 1. This is okay, right? I just substituted this value, I get this. Any problem up to this point? It's just simple derivation, okay? Now we can divide this into two parts, 0 to infinity e to the power minus y square divided by 2 square root of 2 pi dy minus please don't talk. So we have 0 to infinity e to the power minus y square divided by 2 1 plus 1 over gamma divided by square root of 2 pi dy. Okay. Now if we solve this, this is what? This is just the normal distribution being integrated in the half. So we will have this value half. If we integrate from minus infinity to infinity, we will get 1, and we integrate from 0 to infinity, we will get half. Okay. And what about this? This also, let's assume this value to be, let's say 1 plus 1 over gamma is equals to 1 over sigma square, let's say. Okay. So what we'll have to do? We have to here multiply and divide by sigma square. Okay. So this value also will become half. So what we will get? This sigma will come above, sigma divided by 2. And what is this sigma value? Okay. This you get. So this integration will become like 0 to infinity e to the power minus y square divided by 2 sigma square divided by square root 2 pi sigma square dy, and this sigma will come here. Okay. So this is what? Just the PDF of quotient we integrated from 0 to infinity. So its value will be half. So we divided by 2. And the value of sigma is like this. So what we will get finally? 1 by 2 1 minus square root gamma divided by 1 plus gamma. Okay? This is the same thing that we have to prove. Okay? Any doubt here? Now this value we can write for high SNR. So I can write here 1 by 2, 1 minus 1 plus 1 by gamma to the power minus 1 by 2. I am writing the value as same it is. Okay. Now I can put the since gamma is high, this value is very, very low. So I can put the high SNR, the approximation for this 1 by 2, 1 minus 1 minus 1 by 2 into 1 by gamma. Okay. So which comes out to be what? 1 over 4 gamma. Okay. So this is the high SNR approximation. Okay. So the next question, any question here? Yeah. Y equals to from this value to this? This one. So this limit represent the, we take the strip, the horizontal strip. It represents the horizontal strip. So I change the limit of integration. So I took the vertical strip for integration. I mean it's vice versa, sorry actually. So this represents the vertical strip and I took the horizontal strip. Okay, so in horizontal strip it goes from 0 to infinity, this value of y, and the value of x goes from 0 up to this point. And this line is y equals to square root 2x gamma. And we solve for the value of x, I will get y square divided by 2 gamma. Okay? So it's just a changing the order of integration. No, these terms will not be affected. We are just changing the order of integration. This term will not be affected. So this is the similar thing that is taught in the mathematics first year courses. If you just go and you will find out, like this is the same thing. Nothing fancy here. If you want, I can tell you more about it. Okay. So the third question is a precise way of saying that the probability of error PE decays like 1 by SNR with increasing SNR is the following. Limit, let me clean this. The third question. So limit probability of error into SNR or when SNR tends to infinity is equal to C. So where C is the constant, identify the value of C for the Rayleigh fading channel. Okay, so here we are getting 1 by 4 gamma. Okay, so if we put like this, limit gamma tends to infinity, our probability of error is 1 by 4 gamma and SNR is gamma, which is comes out to be 1 by 4, which is the value of C. Okay. Okay, any question here? Okay, now let's move to the question number 4. You are, or everybody has questions, right? So you can look at them, okay? Question number 4, now we want to test how robust the above result is with respect to the fading distribution. So let H be the channel gain and mod of H square be an arbitrary continuous PDF Fx, satisfying Fx, F0 is greater than 0. Does this give enough information to compute the high SNR error probability like in previous part? Okay, so earlier we assumed this to be exponential distribution, right, mod of H square. Now this question is saying we do not know about the distribution of mod of H square. What we will do? Does we still get the same answer or not? So for that, let's just compute this, because we have to finally see this product, gamma into PE. So which is equal to gamma expectation Q value. Let me clear this. Square root of 2 mod of H square into gamma okay, so which comes out to be, so we have Q square root 2 x gamma, and the PD of this I don't know, so I will write here Fx dx. Okay. Now what can I do here? I can do the change of variable. Let t equals to 2x gamma. Okay. So dt is equal to 2 gamma into dx. So what will I get here? So gamma is here. So factor of 2 will come. So gamma dx equals to dt by 2. So 1 by 2 q t f x, instead of x I have to put t divided by 2 gamma into dt. This is okay, right? Now we have to do this limit. If we have to find out our probability of error decreases by 1 by SNR, this is the way to check it, okay? So if we have to check this probability of error, if we don't know the probability distribution of mod of H square, is this still decreasing by 1 by SNR, what we have to do, we have to compute this product and take the limit, and if we find out whether this is constant or not constant, okay? So if we put now limit gamma tends to infinity, what we will get? Let me write here limit gamma tends to infinity, gamma into PE is equal to what? We have 1 by 2, and so gamma tends to infinity, this will go to 0. So F0 will come outside, and we have QT dt, and the limit here will be, so this H square is a positive quantity, so limit here will be 0 to infinity. Here we have made change of variable, the limit still remain from 0 to infinity. Yes, square root will be there. Denominator of 2. So t equals to 2x gamma. One by 2 is still there. Okay. So 1 by 2 is still there. So what I'm saying here, the limit will be 0 to infinity, and we have square root of t here. Okay. So f naught is coming outside. So this value will be, so we are integrating like 0 to infinity this q function. So its value will be approximately equal to half. Okay. So we can write f naught divided by 4. Okay. So we get this constant. This is constant. So if it is coming constant, then we can say our probability of error is decreasing by 1 by SNR, even if the fading, this fading distribution is some different than exponential distribution. Okay. Okay, clear? Any question here? Okay, we move to the next question then. Next question says, consider the Rayleigh fading channel and show the following. Question number 5. Show the following probability mod of h square into SNR. Let's say SNR is gamma is less than equals to 1. We have to calculate its value. Okay. So mod of h square is exponentially distributed, right? So this value we can write like mod of h square less than 1 by gamma. And this exponential distribution, it means this value is positive. So 0 to 1 by gamma we have to go, right? An exponential distribution is lambda e to the power minus lambda x. So e to the power minus x dx. Now we put this value e to the power minus x divided by minus 1 by gamma 0, which comes out to be e to the power minus 1 by gamma minus plus 1. Okay. Now this is saying it should be 1 by SNR plus O 1 by SNR square. Okay. So we can just expand. So 1 minus, we can expand this 1 minus 1 by gamma plus 1 by gamma square 2 factorial plus and so on. Okay. So we expanded this exponential into a series. So what we will get 1 over gamma plus some term based on 1 by gamma square. Okay. So this is the solution for the 5th question. Now let's come to the 6th question. Consider an L repetition code with Rayleigh fading channel and BPSK modulation. So L repetition code. So let's say y equals to hx plus w. So where we have L repetition code, the error probability condition on H can be written as like this. Okay? So this expression you can obtain similarly that we obtained for the BPSK. Okay? So do you want me to derive this expression that is written here, or you can get the expression? Should I derive it? Okay. So we have the repetition coding. So this is L cross 1, this is L cross 1, and this is L cross 1. Okay. So the same thing is being sent L times. Okay. So that's why it is repetition coding. Okay. Now let's say BPSK modulation. So X will be plus minus square root of P. Okay. So we can write probability of error condition on H. So H is fixed at the moment. Okay. After we derive with H fixed, we will take the expectation on H. Okay. So which will be equal to the probability of error. It means we have to multiply with H Hermitian Y divided by norm of H, and X is BPSK, so we have to take the real part, and this should be greater than 0 if we are transmitting X equals to minus square root of P. So this is the probability of error when we are transmitting X equals to minus square root of P, and we are favoring the positive part. This thing is okay? Any question here? Okay. So this thing is so we can write this real of H Hermitian Y greater than 0, X is equals to minus square root of P, and we can put the value of Y. So real of H Hermitian H into X is equals to square root of minus of square root of P plus H Hermitian W greater than 0. Okay. So that comes out to be probability. So this is H Hermitian H is real, and this is also real, so we can take it outside. So H Hermitian H into minus square root of P plus real of H Hermitian W greater than 0. Okay. So this, what is the statistics for this one? Okay, we have to find out the statistics. So real of H Hermitian W. So its mean will be 0, since the mean of noise is Gaussian with 0 mean and variance. So let's say W is Cn 0 comma sigma square I. So it means W has 0 mean and sigma square variance, and its entries are uncorrelated. Okay. Identity means its entries are uncorrelated. Between the entries there is no correlation. Okay. Now we have to find out this. So let's find this another way. H Hermitian W plus W Hermitian H divided by 2, and we have to take the expectation. So we have to find out the variance. So variance of real of H Hermitian W is equal to expectation of, so real of H Hermitian W square minus, so it's mean is 0, so it will be just the square. Okay. So expectation. So if we just put that value, so we can find out the way that the way we did yesterday. We can also find it this way. Okay. Both are okay. Both will give the same answer. So H Hermitian W plus W Hermitian H. So this is square divided by 4. So what will I get here? Expectation. So it will be long one. Square 2. So H Hermitian W square plus W Hermitian H square plus 2 W Hermitian H square divided by 4. So 1, 2, 3, 4, which is equal to expectation of H Hermitian W square, which is equal to expectation of H Hermitian W Hermitian H, which is equal to H Hermitian expectation W Hermitian H, which is equal to sigma square I H Hermitian, which is equal to H Hermitian H into sigma square. Okay. If we do the square here, I will get one term, and twice into this term, 2 plus 1 plus 3, 4. Yeah, that's it. Okay. So this is just one way. You can derive also, like assuming real part and imaginary part. You can do by that way also. Okay. Both will give the same answer. Okay, so now let's come to this here. So real part of this, H Hermitian W greater than H Hermitian H square root of P, and this value is n 0 comma H Hermitian H sigma square greater than H Hermitian H square root of P, which is equal to probability, we can take it outside, norm of H into sigma n 0 comma 1 greater than H Hermitian H, we can write it mod of norm of square root of P, which is equal to probability n 0 1 greater than norm of H square root of P divided by sigma square. Okay. Is okay. Now we will have this as Q value H square P divided by sigma square root this. Okay. So this is the same thing we are getting. We miss somewhere factor of 2. Okay. The same thing we are getting, but factor of 2 we have missed somewhere. Okay, so there will be a factor of 2 we have missed somewhere. Okay, I will come back to it. So now with given this H, we have to take the expectation of q square root 2 norm of h square into gamma. I am calling gamma as the SNR. This is the probability of error. And we have to calculate this. So one thing, we earlier note that mod of h square is exponentially distributed. Now if we have multiple random variables, that's the summation of it, that distribution is chi square. Okay? So the chi square has two parameters. One is the variance and second is the degree of freedom. The degree of freedom depends of how many parameters are added here. Since h is, so if let's say, if we have some xi complex random variable, let's say n01, okay, and let's say I equals to 1 to n, okay. So mod of xi square, summation of it will be chi square distributed with how many degree of freedom? N degree of freedom, okay, and with the variance 1, okay. Now here h is complex and we have how many elements here? L elements here. So total how many elements? 2L elements are here, okay. Is this you are understanding, okay, right? So we have chi square distribution, h square is equal to summation I mod of hi square will be chi square distribution with 2L degree of freedom, okay, and its variance will be what? Half the variance of each of the entries. So if h is distributed Cn01, okay, then its real part and imaginary part both are counted as separate, okay. So it will be 1 by 2 and 1 by 2, okay. So now we can write this expectation as x equals to 0 to infinity q square root of 2 x gamma into x to the power L minus 1 e to the power minus x divided by L minus 1 factorial into dx, okay. So this is what? This is the PDF of chi square distribution. This is the PDF of chi square distribution, okay. Now we do the similar procedure. We have the integration for x. We write the integration for this square root of 2 x gamma to infinity and e to the power minus y square divided by 2 y square divided by 2 divided by square root of 2 pi into dy, and this thing x to the power L minus 1 e to the power minus x dx divided by L minus 1 factorial, okay. Now with these two integration we will do the same thing that we did earlier, changing the order of integration, okay. here, so we have this line and x is going from 0 to infinity, so it is vertical strip, and y is going from 2 to infinity, so we have to take horizontal strip. So this is the new strip. So this comes out to be y equals to 0 to y equals to 0 to infinity, and x is equals to 0 to up to this line, that is y square divided by 2 gamma, and I write the same thing here. This is for x, so let's write for x term first. So x to the power L minus 1 e to the power minus x divided by L minus 1 factorial dx, then e to the power minus y square divided by 2 divided by square root of 2 pi into dy. So this integration we can solve it. Okay. So how we will solve it? By integration by parts. Okay. So y equals to 0 to infinity so let me give you an example of integration by parts, then I will write the direct answer for this. Okay. So if we have some x square e to the power minus x dx, so how will we solve it? So if we solve this, we will have 3 terms. Okay. So first we will have x square e to the power minus x dx, first part, and second integration of second part, minus integration of first part, then differentiation of this, that is 2x, and integration of that, right? Then for this also I can divide this into 2 parts. Okay. So I will have 2x, then integration of this part, so e to the power minus x, it will remain the same, it minus will come, so plus will come here. Then minus we will have 2 here into differentiation of 2x is 1, then we have e to the power minus x integration of this, so it will become plus dx. Okay. So one term we will have for x square, one term we will have for x, and one term we will have for e to the power minus x. Okay. So this way 3 term will come. Okay. So whatever the power we will have x, we will have the integration that many times, plus 1. Okay. So that way we can solve this. So if I solve this, I will get this. Okay. So each time I will get x to the power decreasing. Okay. So that x to the power is coming here. I have put the limit from y square divided by 2 gamma. So that limit is coming here, e to the power x, and this factorial is coming, since it will be this integration will be done many times. So this factor will come here. Okay. You can try yourself also. Okay. So then we will get e to the power minus y square divided by 2 square root of 2 pi dy. Okay. So this is a standard integral, the solution of this. Okay. Now, so the first integration, second integration, we will do separate. So e to the power minus y square divided by 2 divided by square root of 2 pi 0 to infinity dy minus summation L 1 y L factorial and we have integration y equals to 0 to infinity, and we have 2 gamma to the power L y to the power 2L into e to the power minus y square divided by 2, 1 plus 1 by gamma divided by square root of 2 pi into dy. So summation is here, e to the power, this term are here, y square 2L here, and 2 gamma to the power L here, L factorial here, square root of 2 pi here, dy is here. Okay. So this term is what? This term is the expectation of this when y is Gaussian. Okay. So this is the 2Lth moment of Gaussian random variable. So 2L means this is even. So this is the even movement of a Gaussian random variable which has this much of variance and 0 mean. Okay. This term, okay, 2Lth moment of n0 comma this. So let's say this is let's say sigma square. So this I can assume 1 by sigma square is equal to 1 over gamma plus 1. Okay. So I can multiply here sigma square here. Okay. So sigma will come here. This part is 1 by 2. So I will write here 1 by 2 minus summation L. I have 1 over L factorial 2 gamma to the power L, and this moment. So moment you can check online, or you know the moment generating function. The moment generating function of a Gaussian distribution is like this: e to the power mu t plus sigma square t square divided by 2. Okay. So this is a moment generating function. You have to differentiate it if you want to get the 2Lth moment. So you have to differentiate 2L times. You will get that much moment for Gaussian distribution. Okay. So since mu is what? Mean. Mean here is 0. So what will you get if you have, let's say I am calculating the pth moment. For pth moment. For pth moment, if p is equals to odd, I will get the moment is equals to 0. If p equals to even, I will get the moment sigma to the power p into p factorial divided by 2 to the power p by 2 into p by 2 factorial. Okay. So here we are multiplied with 2. So this is even. So we will get this value. So this value we will put here. Okay. So we will have sigma here. I will write here sigma, and this value sigma to the power p, sigma to the power 2L into 2L factorial divided by 2 to the power L into p is equals to 2L, so L factorial. Okay. So I will get this expression. And of course this 1 by divided by 2, because this is 0 to infinity. Okay. So I can write 1 by 2, 1 minus summation over L. So I have 2L, L, L. So I can write in terms of combination. So 2L, L, and this is taken care of. then I have sigma to the power 2L plus 1. Then I have 1 by 2 is outside, 2 to the power 2L sigma to the power, sigma is what? Sigma is equals to gamma over 1 plus gamma, okay, square root of it, right. So this term is taken care of, this term is taken care of, and gamma to the power L, gamma to the power L, this term I have merged with it, this term taken care of, this one, okay. So I have gamma over 1 plus gamma to the power 2L plus 1, 2L plus 1, and I have gamma to the power L here. So I can write this as so this is the answer if we want to get in terms of SNR. But if you see the question, it is calculated in terms of mu. Mu is equals to SNR over 1 plus SNR, the same thing as sigma. Okay. So if I write this in terms of mu, I will get something different, that is equal to so I will get mu times 1 minus let me do it from scratch 12. So what will I get there? I will get mu here, then mu to the power 2L, mu to the power 2L. So here we can calculate the gamma. So mu square is equals to gamma divided by 1 plus gamma, and 1 by mu square is equals to 1 plus 1 by gamma, and 1 by gamma is equals to 1 minus 1 by mu square. Okay. So we have gamma here. So I can write here 12 plus 1 here, and this gamma 1 by gamma I can write 1 minus 1 by mu square to the power L. So it is just the rearrangement of different terms to get the answer. So we have mu is equal to 2L, so we will take this, and so mu 2L plus 1 divided by mu to the power L here, and 1 minus, so we have 2 to the power 2L to the power 2L, 1 minus mu square minus 1 to the power L. Okay. So this mu L will be cancelled out. I will get I will get 1 by 2, 1 minus summation L 2L L mu to the power mu to the power L plus 1 divide and 1 plus mu to the power L divided by 2, 1 minus mu to the power 2 divided by L. Okay. So this is the answer we will get. Okay. So should I explain it again or this derivation or summarize it again? So we started from this expectation of Q, that random variable, okay, that has the chi-square distribution. So chi-square distribution we write it. After that what we did the change of limit, we changed the limit, change the order of integration, and then we solved it, okay. In between we get this x into exponential term, integration of that. So we solved it. So it comes in terms of summation, okay. And after the summation, we just rearrange the terms to get the answer, okay. So here we just note that our limit is going from 0 to infinity. Since it is going 0 to infinity, the half term will come here, okay. So here, since this term is here, it gives rise to the moment. So for the moment, we use the moment generating function. So moment generating function, we note that for even moments, it is 0 when mu is 0, okay. For when mu is 0, when p equals to odd, it is 0, okay. When p is equal to even, we are given, we will have this value, okay. So this value we have substituted here, and we get this expression. And I did only rearrangement of the term. So I find out the answer in terms of this value that I get from this when I was substituting here, okay. Now this question says we can calculate in terms of mu, that is square root of SNR over 1 plus SNR. So I did square root of 1 plus SNR like this, and every gamma I have to substitute in terms of mu. So I calculate the gamma in terms of mu, and I substituted that value here, okay. So here 1 by gamma is coming here. So 1 by gamma I calculated it to be 1 minus 1 by mu square. So I substituted here, okay. So then I rearrange the term. So I will get mu square minus 1 here to the power L, and this term I will get like this, and mu to the power L. So 2L will come here. So it will be 2L. So since this is mu square will go here, mu square minus 1. So 2L will cancel out. I will get only mu here. So mu here only, mu to the power 1, okay. And we have 2 to the power 2L, that is coming from all of the above from here. 1 to the power L here, 1 to the power L here, okay. So mu square minus 1, I can write it as 1 plus mu and 1 minus mu. So mu minus 1 will come here, mu minus 1 and mu plus 1, okay. And so this 2 I have distributed in terms of two values here, 1 to the power L here, 1 to the power L here, and this mu term remain here, and this is the expression, okay. So this gives the same value as this expression here, okay. Now it also says something about approximation, okay. So let's derive some approximation. Is this okay? So here, if you want to do this derivation by your own, you need to know what is the Gaussian movement. You need to know the about the Q functions thoroughly, okay, and the chi-square distribution. Okay, rest of it is simple calculus and rearrangement of terms. Okay. Let's clean this thing. So probability of error, we have to approximate by 2L minus 1 L 1 by 4 gamma to the power L, and at high SNR we have to calculate the deep fade. Okay. So let's take the expression that is given here, that is P is equal to 1 minus mu divided by 2 summation L equals to 0 to L minus 1 L minus 1 plus L 1 plus mu divided by 2 to the power L. Okay. So here, if we want to find out this, we have to do the similar thing that we did earlier. P into SNR, it should. So mainly we have to find out for the high SNR. So let's approximate 1 plus mu divided by 2, which is equal to 1 by 2, 1 plus 1 by gamma to the power minus 1 by 2, okay, which comes out to be, so this goes approximately infinity. So for high SNR I am writing, so 1 by 2 and so this goes 1 plus mu is 1 plus gamma by 2. Gamma is infinity, so 1 plus 1, which is equals to 1, okay, when gamma tends to infinity, okay, and 1 minus mu divided by 2 is equal to 1 by 2, 1 minus 1 plus 1 by gamma to the power minus 1 by 2 is equal to 1 by 2, 1 minus 1 by 2 gamma, which is approximately equal to 1 by 4 gamma. So with this I can write this 1 minus mu divided by 2 is equal to 1 by 4. So 1 by 4 gamma to the power L summation L minus 1 plus L, and this thing is 1, so it is 1 here. So this value comes out to be 2L minus 1 L into 1 by 4 gamma to the power L. Okay. So this approximation is clear, right? So I just pushed gamma tends to infinity, so this becomes 0, so this becomes 1, 1 plus 1 is 2, 2 into 2 is 1. And for high SNR, this term is very low, so I put here, so 1 minus 1 plus nx approximation I put here, so 1 minus 1 by 2 gamma, 1 cancel out, I will get 4 gamma. So I put these two values here, I will get this, and this term is a constant which comes out to be this, I will get this here. So what this term shows is that this probability of error is decreasing with SNR to the power L. So this L is the diversity factor, diversity order, okay? So next we have to calculate this deep fade. So probability of deep fade So I have to use the similar chi-square approximation, chi-square distribution here. So e to the power minus x into s to the power l minus 1 divided by l minus 1 factorial into dx. Okay. So what will I get here? So if so x is when x is very small, what we can do, we can neglect this term e to the power minus x, and I can write here like directly like this. So what I am doing here, this is the approximation. This thing you can also calculate in terms of summation. So like we did the earlier, you can also calculate this in terms of summation. But this value is very small. Since if we are talking about high SNR, then gamma is very high. Okay? So this value is very high and this is 0. So this value will be very small. Okay? So we can calculate just for the rest of the term. Okay? So that comes out to be x to the power l divided by l into l minus 1 factorial, which is 1 by gamma and 0. So which is 1 by gamma to the power l into l factorial. So this also shows that there is a diversity factor of l. Okay. So after that derivation, in these two approximation, there is no problem, right? Approximation are easy. Okay. So let's move to the next question. So this is the high SNR approximation. You can also derive in terms of summation, integrating by parts L minus 1 times, you will get the same answer. Okay. So this is just to get the insight quickly. So in the next question, question number 7, we have to show the value of the Q function is bounded by the bounds of the Q values we have to prove. Okay. So let's prove one bound. So before that, let's say A is between 1 to infinity. 1 to infinity. Okay. So 1 by A will be between 0 to 1. Right? So 1 by A will be less than 1 and 1 by A will be less than 0. So 1 minus 1 by A to the power 4 will be greater than 0 and less than 1. Okay. If I take the a to the power 4, it will still be less than 1, and if I take here, so this will be greater than 0, and if I take 1 minus, so it should be greater than 0 here. Okay. This is okay. We will use this to solve. So for example, QA is given by A to infinity e to the power minus t square divided by 2 divided by square root of 2 pi dt. Okay. So here we have, let's say 1. So this 1 is greater than 1 minus a to the power 4. So I will put here 1 minus a to the power 4 here, e to the power minus t square divided by 2 is square root of 2 pi dt. So I can make this into two parts, 1 minus 1 by a square, 1 plus 1 by a square e to the power minus t square divided by 2 divided by square root of 2 pi dt. Okay. So limit here t equals to a to infinity. So t is greater than equals to a. It means 1 by t is less than 1 by a. Okay. So 1 plus 1 by t square will be less than 1 plus 1 by a square. Okay. So 1 plus 1 by a square is greater than 1 minus 1 by a square, 1 plus 1 by t square e to the power minus t square divided by 2 divided by square root of 2 pi into dt. Okay. So this term comes outside and this term we will have here
We'll take break now.
okay.
You want to continue, sir?
Let's finish this question. Okay.
Sir, because the tea will
Okay.
become cold.
Okay, let's take break.
Sorry.
Yeah, let's take break. Let's take break.
Yeah, if tea becomes cold, they won't drink. Yeah, sorry, sir. Real.
BPSK simulation for the relic feeding channel. Okay. So this is the debug mode. So I am running each line one by one. CLC clear, you already know. CLC clear the command window and clear the workspace, delete all the variables. Okay. And RNG1 is to initialize the random number. Okay. Now I go to another step. Since I am doing BPSK, so I have chosen S is equals to plus minus 1. Okay. NS represent number of symbols for the simulation. I have chosen 1E4. It means 10 to the power 4. IRND, it means I am generating.
Please write in comments, sir, so that they will understand.
Okay. I will write comment here. So this is BPSK. BPSK constellation. These are the number of symbols, and these are the number of, I want to generate a data stream. Okay. So I will not transmit only like 1 bit or 2 bit. I will transmit a stream of numbers, right? Plus 1, minus 1, plus 1, minus 1, plus 1, minus 1. For that, I need to generate a random stream. Okay. So this command generates random number. Random stream generate. So
Means integer or something like that.
yes. So this rand I command generates. So if I write 2 here, so I can press F1. So it will give me the information. So rand I2 means it will give me the random number up to 2. So 1, 2. If I write rand I n, so it will give me random number between 1 to n. Okay. And how many random numbers I want to generate? I want to generate 1, ns, the size of the random numbers. So this second argument represents the size. So ns is equal to 10 to the power 4. So this will generate 10 to the power 4 random numbers 1, 2, 1, 2. Okay. Let's check it whether it's generate or not. Okay. Let's go to the next step. So here you see this is showing a preview of some of the values of IRND variable. So this is 1, 2, 1, 1, 1. Okay. So this is generating random values between 1 and 2. Okay. Why we are generating 1 to 2? Because our BPSK has constellation has only 2. So if I write here in the next line x equals to SIRND, so it will generate +1, -1 for all of the stream. Okay. Let's go to this step. So this x will be -1 +1. So this will generate the whole stream for 10 to the power 4 numbers. Okay. This part is clear up to? So this is what? This is BPSK stream. Now what I am doing here, I am generating here noise. Okay. So when I transmit one bit +1 or -1, I will get that much noise. So I am generating 10 to the power 4 values for noise. So noise is complex Gaussian distributed. Okay. And each part has half the variance. Okay. So this is the rand and generate what? Gaussian distributed random variable with 0 mean and unit variance, but each has half. So I will divide by square root of 2. So its variance become half. So half and half becomes 1. So this is the imaginary part, this is the real part. Total the variance is 1 and mean is 0. Okay. So this is the way we generate what? Complex Gaussian random variable for noise. Okay. So let's move to the next line. So this is the dimension of it is 1 cross 10 to the power 4, and this is a complex variable. Okay. So these are complex values. So this NH, I have taken another variable because we have another random variable that is called the channel. So channel we will also generate some values because we have to take the average. So first we check the probability of error for fixed channel, then we take the average. The thing we have done in the when deriving the derivation, doing the derivation. First we choose the fixed H, then derive the probability of error, then we take the expectation over H, right? So for that we take an NH equals to 100, we will average over 100 channel realization. Okay. So this represent number of channel realizations. Okay. This one is noise, circularly symmetric Gaussian noise. Okay. So next I generate the channel. Channel I generate with CN01 variable, that is 0 mean, unit variance, or the size of it is 100. Okay. So this is the real part and this is the imaginary part. I have to write one I here for the imaginary part, and then square root divided by 2, because each will have real part and imaginary part have half the variance. Okay. So this is the way I will generate the channel. Okay. And how many channels I will generate? I have chosen number of realization to be 100. So I will generate 100 cross 1 vector for that. So this H will be, since I have made some change here, I have to save it and rerun it again. So this H is 100 cross 1 vector. Okay. Now I want to plot my bit error rate versus the SNR. Okay. So the SNR, I will change the transmit power. So transmit power I have chosen between 0 to 40 dB. Okay. So this linspace command generates values, it will generate 15 values between 0 to 40 equally spaced. Okay. So it will generate 15 values. So this PDV has 15 values, and minimum value is 0 and maximum value is 40, and these are equally spaced. Okay. So NDB, I have chosen the length of PDV, that is 15. Okay. Next, I chosen the variable PE for probability of error that I going to assign. So I have just initialized that variable. So I have two indices here, one for NH for each channel realization and each transmit power, that is NDB. Okay. So for each transmit power IDB equals to 1 to NDB, I am running the loop, and for each transmit power I am assigning P2. So this above 0 to 40 was in dB. So I am converting it dB into normal power by using this function dB to pow, and PDB is my this variable, and I am choosing particular index IDB which is ranging from 1 to NDB. So in each iteration it will give me one of the values from the array, that is PDB, and it will convert it to power, okay, from dB. Okay. So let's go to next line. So this P is equals to 1 here. Why 1? Because the IDB is 1 and PDB is initially 0. So 0 dB is 1. Okay. So now I am doing for each channel realization. Each channel realization I am running the loop IH equals to 1 to NH. So this is my loop index IH. Okay. So I have taken channel H equals to IH. I took the channel one by one, and I have written the equation here, y equals to H into X into square root of P, that is the transmit power, plus noise. Okay. H is my channel, and H is my transmitted vector, +1 or -1, and the square root of E is my power, and W is my noise. So this is what I will receive. Okay. So what is the size of it? Y equals to 1 cross 10 to the power 4. Okay. So what is the size of H? H is 1 scalar value. What is the size of X? X is 1 cross 10 to the power 4, and this is also scalar, and W is 1 into 10 to the power 4. So this, the first thing in this sum, this is a vector and this is a vector. So the output is a vector 1 cross 10 to the power 4. Next, what I have to do? I have to detect it from Y. So the decision rule I explained earlier yesterday. What was I doing? Real of Y divided by H greater than 0. If I have greater than 0, I will choose +1. If I have less than 0, I will choose -1. Okay. So in MATLAB, so this is like a hard decision. So in MATLAB, if I write this, it will give me either 0 or 1. So this is like a Boolean expression. Okay. So this is either true or false. So if I write this, the output of this will be either 0 or 1. So I have to compare 0 and 1 with -1 and +1. So what I have to do here? I have to convert 0 and 1 to -1 and +1. So that's why I have written 2 into -1. So it will convert my 0 and 1 to +1 and -1. Okay. So that way I will get the estimate of my transmitted value. Okay. That is x1. Next, what I have done here? I have written here x1 not equal to x. Whenever x1 not equals to x, those will be true and false. It will come, and mean means it will count those true or false, and it will take the mean value of it. So this will give me the probability of error. This part is okay. So it's just an expression. This will give me the Boolean expression. Okay. So x1 is what? 1 cross 10 to the power 4, and x is also 1 cross 10 to the power 4. So we can compare both of the vector because both of the length are same, and we will get +1 or -1 accordingly, 0 and 1 accordingly. Okay. So mean means it will take the mean of ones. It will take the sum. So 1 will come when values are not equal. When this condition is true. The condition is what? X1 not equal to X. Okay? Clear? So this will give me probability of error for a particular channel realization. And this loop will run for each channel realization. Okay? So I am collecting all the probability of error for different channel realization in the variable PE for all channel realization and also as well as for all different transmit powers. Okay? Which I have already initialized this variable, and I am taking each value here one by one. Okay? So for example here, let's check this value, what this will be. Evaluate, let's see the command window. So it is showing me 0.0436. This is the probability of error for this particular realization at 0 dB. Okay? If channel realization will change, this value will also change. If noise will change, this value will also change. Power will change, then this value will also change. Okay? So after I have run both of the loops, I will get up to here. So let's stop it and run the whole program and reach up to here. So if I run it, I will get up to here. So I will get this probability of error, which is of 100 cross 15. 100 for what? Number of channel realization, and 15 is for what? Number of transmit power values I have chosen. Okay? Now for each channel realization, I will take the average. So I have written here mean PE, comma 1. Comma 1 means the first dimension. So in a matrix, the first dimension is row wise, second dimension is column wise, and the third dimension is, and so on. Okay? So here I have to take the mean with respect to the channel. Channel is the first dimension. You see 100 here. It is the first dimension. Okay? So after that, I will get how many values? 15 values corresponding to each transmit power. Okay? So each transmit power. Now I can plot this. I have written here figure 1, comma CLF. CLF means clear figure. Figure 1 will generate the empty figure. Now I write here plot PDV, PE, comma 1. Hold on. And then I am in the second thing, what I am doing, I am plotting for any realization, let's say PE second channel realization, I am also trying to see what happens for a particular channel realization. So I am just plotting here, okay, and set GCA Y scale log. So what does it do? It converts the Y scale into the log scale, okay. So it will be a semi-log plot, okay. GCA means get current access, GCA. And then I have chosen to on the grid. So it will turn on the grid. Okay. So I will get this kind of curve. So the blue curve represent my BPSK simulation with Rayleigh fading, and this red curve for a particular realization, channel realization. Okay. Any question up to this point? Huh? Flat fading channel. Frequency selective channel, either we have to use the CDMA or we will use the OFDM normally. Okay. So that thing is different. I mean, that is like a very big simulation. Okay. If we are teaching it, we will cover it. OFDM I can easily OFDM also convert the frequency selective channel into frequency flat channel also. So OFDM is mostly used if we have wideband.
Can I answer that?
Yeah.
Madam, frequency selective, yeah, madam. Why we use flat fading means basically flat fading means we have over the bandwidth of the channel used. quiet response. It is constant value. Huh? Constant value means the constant value we can use it for simulation. Yeah, it is a frequency selective means if it changes like this randomly intermittently. What we have to do, yeah, up to how much our constantness is there, will yeah, like non-linear things we can't use, right? How do we use non-linear things? We split the non-linear things into linear things, small parts, and in that small part it becomes linear. Similarly here also frequency selective means, yeah, up to a little part, little bit of bandwidth only it is constant. Over that little part only we can use. So frequency selective channel means we can use over that flat fading channel. We have to divide the frequency selective channel into flat fading channels. You understand? You understand what I'm telling now? H is constant. Yeah, that again depends on the channel you are using. It depends on the channel. If you are using F1 frequency, F1 carrier frequency, that will be having some fading. If you are using F2 carrier frequency, that will be having different fading because it is frequency selective. So based on that you have to use. Why CDM and WebDM can be used in frequency selective channel means we have variation. In WebDM what we try to do, we try to reduce intersymbol interference, right? By adding circuit repeats or by taking the smaller sub-channel bandwidth. The smaller sub-channel bandwidth. So that's why that WebDMA is converting the frequency selective channel into flat fading channel. That's why we are able to use, even though it is a frequency selective channel, we are able to use, yeah, like a sort of dividing non-linear into linear things. We are able to use even frequency selective fading channel also. Yeah. Yeah, piecewise linear. Yeah. You understood now? Okay, sir.
Okay. Any question here in this BPSK simulation? This is easy, right? Okay. So I have another simulation that is for QPSK. Okay. This is slightly different. Most of the part is similar. Yes. Yes, more symbols will be there. So this is just for a point-to-point system. One transmitter, one receiver, single antenna. Okay. So, okay, let's continue. So first is CLC clear. Then we define the QPSK constellation. So QPSK constellation has 4 points. Okay. So these 4 points are -1 -I, -1 +I, +1 -I, +1 +I. Square root of 2 for the normalization. Okay. So 10 to the power 4 number of symbols, and these are the to generate the random stream. So here I have written here length of S. So length of S is 4. So it will generate the random number from 1 to 4. And how many random number it will generate? 1 cross 10 to the power 4. NS is 10 to the power 4. So this X will be 1 cross 10 to the power 4. So let's run this and see. So this IRND, it is showing some preview. 2, 3, 1, 2. Okay. So it will generate between 1 to 4. And the value of X is accordingly. Okay. So next is W. So this is the noise, the same way. Then I choose a 100 channel realization. Then I generate the channel in the same way. Number of transmit power values I have chosen to be 15 between 0 to 40 dB. And dB is the length of this, that is 15. And PE is the probability of error. In that variable, I will assign all the values. So I just indented the code so that it can be easily understandable. So let's run up to here. Okay. So we are now here. So let's run it. So for each transmit power, I choose the index IDB equals to 1. It will convert to the from dB to power. And for each channel realization, I will write the same equation, y equals to hx into transmit power plus noise. And here what I am doing here, I am doing here ML decoding. Okay. In ML decoding, what we have, y minus hx, we have to find out the x over all possible values. Okay. So here y is my 1 cross 10 to the power 4. Okay. And h is a scalar. H should be complex. Okay. One I is remaining here. So h is complex, and then s is what? S is our vector 4 cross 1. For each y, I will check whether this difference is minimum for which of the values. Okay. Whichever value of s gives me the minimum, I will choose that value. Okay. So if I select this and run this, evaluate, I will get some values like this. So the size of it, how many it will be? 4 cross 10 to the power 4. For each value, I am comparing with 4. Now, for